Hello there, curious soul. Welcome back to this little corner of wonder we've created together. I'm so glad you've found your way here tonight. I know you've had one of those days, maybe your mind is still spinning from the rush of everything. Thoughts bouncing around like restless satellites. You're not alone in feeling this way. So many of us carry the weight of our busy worlds, searching for something that reminds us there's magic beyond our everyday concerns. Tonight, I have something gentle for you, a question that's been floating through my mind like a whisper from the cosmos. What if I told you that right above your head, there are 40 secrets so beautiful, so quietly extraordinary, that most people have never even heard them? Before we begin this journey together, take a moment to let our little community know you're here. A simple like, a gentle comment about what brought you to this moment. It helps us all feel a little less alone under this vast, star-filled sky. Now let yourself settle in, feel your shoulders drop just a little. Let your breathing slow to match the ancient rhythm of planets in their dance. There's nowhere else you need to be right now. Our solar system? It's like a cosmic lullaby that's been playing for billions of years. Tonight we're going to drift through this celestial neighborhood of ours, discovering hidden stories written in starlight and shadow, in the gentle pull of gravity and the whispered songs of distant moons. Picture yourself floating weightless and peaceful, among worlds that hold secrets more wondrous than any dream. Each fact we'll explore together is like finding a pearl of light in the soft darkness of space. Beautiful, surprising, and somehow perfectly placed, just for you to discover. Fact 1. The Sun holds 99.8% of all mass in the solar system. Have you ever tried to imagine something so massive that everything else around it becomes essentially meaningless? Picture yourself standing in your backyard, looking up at the sun filtering through the leaves of a tree. That warm, familiar star hanging in our sky, the same one that's warmed countless generations before us, holds a secret that puts our entire cosmic neighborhood into breathtaking perspective. Our sun contains 99.8% of all the mass in our solar system. Let that sink in for a moment. Every planet you learned about in school, every moon that orbits those planets, every asteroid tumbling through space, every comet with its magnificent tail streaming across the darkness, every grain of cosmic dust drifting between worlds, all of it combined, everything we think of when we imagine our solar system, makes up less than 0.2% of the total mass. To understand this incredible dominance, imagine you're at a cosmic weighing station. If you could somehow gather up Earth, Mars, Venus, Mercury, Jupiter, Saturn, Uranus, Neptune, and Pluto, along with all their moons, including our own moon that seems so substantial as it lights our nights, and then add every single asteroid in the belt, every chunk of ice in the Kuiper belt, and every wandering piece of debris floating in the vast spaces between worlds, the entire collection would barely register on a scale compared to our sun. This isn't just a number in a textbook. It's a humbling reminder of our place in the cosmic dance. We often think of planets as the main characters in our solar system's story, but they're more like supporting actors in a drama dominated by one overwhelming star. Jupiter, that massive giant we call the king of planets, seems enormous to us, and it is, capable of fitting over 1,000 Earths inside it. Yet even Jupiter, with all its moons and magnetic majesty, is nothing more than a rounding error in the sun's cosmic accounting. The sun achieved this dominance through a process that began 4.6 billion years ago, in a swirling cloud of gas and dust called a nebula. As gravity pulled material together, the center of this cosmic whirlpool grew denser and hotter, eventually becoming our sun. The leftover material, that tiny fraction we've been talking about, formed everything else we see when we look up at the night sky. This mass difference explains so much about how our solar system works. It's why all the planets orbit the sun, rather than wandering freely through space. It's why comets that venture close to our star are pulled into spectacular elliptical paths. It's why spacecraft leaving Earth must fight against the sun's gravitational pull to reach other worlds. The sun's overwhelming mass creates a gravitational well so deep that it governs the motion of objects, billions of kilometers away. Think about this. The next time you feel the sun's warmth on your face during a quiet morning, you're not just experiencing light and heat from a nearby star. You're feeling the influence of an object so massive it holds our entire cosmic neighborhood in its gravitational embrace. Every planet, including our Earth, is like a small boat bobbing in the wake of a massive ship, following paths determined by the sun's incredible bulk. This cosmic perspective can be oddly comforting. In a universe that often feels chaotic and unpredictable, there's something reassuring about the sun's steady, overwhelming presence. It's been burning with reliable consistency for billions of years, and it will continue to do so for billions more. Its massive gravitational influence keeps our planetary family together, ensuring that Earth maintains its perfect distance, not too hot, not too cold, in what astronomers call the habitable zone. So when you look up at our familiar daytime star, remember that you're witnessing the cosmic equivalent of a gentle giant. Despite holding almost all the power in our solar system, the sun shares its energy generously, sending light and warmth across vast distances to nurture life on our tiny world. We are, quite literally, children of this massive star, orbiting in its light, warmed by its energy, held in place by its gravitational embrace. In the grand cosmic perspective, we're all just riding on a small piece of that remaining 0.2%, spinning through space around a star that defines our very existence. Fact 2. Venus spins backwards. Imagine waking up tomorrow morning and discovering that everything familiar had been turned upside down. The sun, instead of rising in the east as it has every day of your life, slowly creeps up from the western horizon. This isn't a dream or some cosmic mistake. This is everyday reality on Venus, our neighboring world, that decided to dance to its own rhythm in the most dramatic way possible. Venus spins backwards, while every other major planet in our solar system rotates in the same direction, what astronomers call prograde rotation. Venus chose rebellion. It spins in retrograde, meaning if you could somehow stand on its cloud-shrouded surface and survive the crushing atmosphere and hellish temperatures, you'd watch our sun rise in the west and set in the east, painting the sky in reverse of everything we know. But how does a planet end up spinning backwards? The story likely begins billions of years ago during the chaotic early days of our solar system when worlds were still forming and massive objects regularly collided in cosmic pinball games. Scientists believe Venus may have been struck by one or more enormous asteroids or even a planet-sized object. Impacts so powerful they literally knocked the planet's rotation into reverse. Imagine a spinning top that gets hit so hard it starts spinning the other way. That's essentially what happened to Venus on a planetary scale. This backwards rotation creates a world of strange consequences that would bewilder any visitor from Earth. On Venus, the Coriolis effect, the force that causes hurricanes to spin counterclockwise in Earth's northern hemisphere, works in reverse. Weather patterns, if Venus had weather as we understand it, would behave like mirror images of terrestrial storms. The very physics of atmospheric circulation follows rules that seem alien to our Earth-trained intuition. The backward spin also affects Venus's relationship with the Sun in subtle but profound ways. While Earth experiences relatively even heating as it rotates, Venus's retrograde motion creates different patterns of solar heating. Combined with its incredibly thick atmosphere, 90 times denser than Earth's, this backwards rotation contributes to Venus's uniform temperature distribution. Whether you're on the day side or night side of Venus, the temperature remains virtually the same, hot enough to melt lead. What's particularly fascinating is how this retrograde rotation interacts with Venus's orbit around the Sun. From our perspective on Earth, Venus appears to go through phases like our Moon, but its backward spin creates unique viewing angles and timing. When Venus is closest to Earth, it's showing us its night side, while when it's farthest away on the opposite side of the Sun, we see its day side. This cosmic choreography, influenced by that ancient backward spin, creates the familiar pattern of Venus as both morning star and evening star. The backwards rotation also means that Venus has the longest day of any planet in our solar system relative to the stars, what astronomers call a sidereal day. If you could somehow survive on Venus's surface and had an indestructible watch, you'd need to wait the equivalent of 243 Earth days to see the Sun return to the same position in the sky. That's longer than a Venetian year, creating the mind-bending reality where birthdays come more often than sunrises. This retrograde spin has implications for Venus's magnetic field, or rather its lack of one. Earth's magnetic field is generated partly by our planet's rotation, which helps create currents in our molten iron core. Venus's slow, backwards rotation may contribute to its almost complete lack of a magnetic field, leaving the planet exposed to the solar wind and contributing to the loss of any water it might once have possessed. Standing on Earth and looking up at Venus in our evening sky, it's humbling to think about this backwards world. Here's a planet almost identical to Earth in size and mass, orbiting at a distance that should make it habitable, yet spinning in the opposite direction because of some ancient cosmic collision we can only imagine. It's a reminder that the familiar patterns we take for granted, sunrise in the east, sunset in the west, aren't universal laws but accidents of history. Venus's backward spin tells us that planetary formation is a chaotic, violent process where worlds can be literally knocked into new orientations. It shows us how a single ancient event can influence a planet's behavior for billions of years, creating a world where east and west have opposite meanings, where the sun travels backwards across alien skies. Fact 3. One day on Venus is longer than its year here. Picture this. You're planning a birthday party on Venus, and you realize something extraordinary. By the time you've experienced one complete sunrise and sunset, one full day, you could have already celebrated your birthday twice. This isn't science fiction, it's the mind-bending reality of our neighboring planet, where the concept of day and night gets turned completely on its head. On Venus, one day lasts longer than 1 year. It takes Venus 243 Earth days to complete a single rotation on its axis, while it only takes 225 Earth days to complete one full orbit around the Sun. This means a Venusian year, the time it takes to go around the Sun once, is actually shorter than a Venusian day. It's like running a race where you cross the finish line before you've completed your first step. To understand how extraordinary this is, think about Earth's rhythm. Our planet spins once every 24 hours while taking 365 days to orbit the Sun. This gives us the familiar pattern of roughly 365 sunrises and sunsets per year. The relationship between day and year feels natural to us because it's all we've ever known. But Venus plays by different rules entirely. This strange timing creates a world where seasons would be almost meaningless if Venus had seasons at all. On Earth we experience the changing seasons because our planet is tilted on its axis, and we orbit the Sun, creating variations in how much sunlight different parts of our planet receive throughout the year. But on Venus the incredibly slow rotation means that by the time one region has experienced significant seasonal change, multiple years have already passed. The implications become even more fascinating when you consider what this means for anyone hypothetically living on Venus's surface. Imagine trying to establish a calendar system. Would you count years or days as your primary measure of time? Would birthdays be based on trips around the Sun, or on the number of sunrises you've witnessed? The very concept of daily routine becomes abstract when a single day outlasts multiple trips around the Sun. This extreme day-year relationship is intimately connected to Venus's backwards rotation. Not only does Venus spin in the opposite direction from most planets, but it does so incredibly slowly. The combination of retrograde rotation and sluggish speed creates this temporal puzzle, where the planet's relationship with the Sun defies our Earth-trained intuition about how worlds should behave. Scientists believe this slow rotation might be the result of Venus's incredibly thick atmosphere. The planet's atmosphere is so dense, 90 times thicker than Earth's, that it creates enormous atmospheric tides. Just as our moon's gravity creates ocean tides on Earth, the Sun's gravity creates atmospheric tides on Venus. But because Venus's atmosphere is so massive, these tides act like cosmic brakes, gradually slowing the planet's rotation over millions of years. There's also the possibility that Venus's slow spin is the lingering effect of whatever cosmic collision knocked it into backwards rotation in the first place. Perhaps the same impact that reversed Venus's spin also dramatically slowed it down, creating this double anomaly that makes Venus unique among the planets. From a practical standpoint, this day-year relationship would make Venus an incredibly difficult place for any form of life as we know it. Most biological processes on Earth are tied to daily cycles, circadian rhythms that help regulate sleep, metabolism, and countless other functions. On Venus, these cycles would be meaningless. Any hypothetical Venusian organism would need to adapt to a world where the Sun moves almost imperceptibly across the sky, taking months to travel from east to west. The extreme day length also affects Venus's temperature distribution. On Earth, the night side of our planet cools down while the day side heats up, creating temperature differences that drive weather patterns. But on Venus, the incredibly long days and nights, combined with the planet's thick atmosphere, create almost uniform temperatures across the entire surface. Whether it's day or night, Venus maintains a nearly constant temperature of about 460 degrees Celsius, hot enough to melt lead. This temporal peculiarity reminds us that the universe doesn't follow Earth's rules. Venus, our nearest planetary neighbor, shows us that worlds can exist where our most basic assumptions about time, day, and night simply don't apply. It's a place where patience would be essential, where waiting for sunset would require the dedication of multiple generations. Fact 4. Mercury has ice at its poles. Sometimes the universe delights in paradox, creating situations so unexpected they seem to mock our assumptions about how things should work. Here's Mercury, the closest planet to our Sun, racing around our star at breakneck speed, while enduring temperatures that could melt zinc. Logic tells us this should be the most uniformly scorched world in our solar system, yet hidden in the shadows of Mercury's polar regions, protected in craters that never see sunlight, lies something that seems impossible: ice. Actual frozen water, preserved in cosmic freezers that exist just a few hundred kilometers away from some of the hottest surfaces in the solar system. The story of Mercury's ice begins with understanding the planet's unique relationship with sunlight. Mercury has virtually no atmosphere to speak of, certainly nothing that could redistribute heat around the planet. This means that areas in direct sunlight become incredibly hot, while areas in shadow become incredibly cold. But most remarkably, Mercury's rotational axis is almost perfectly upright relative to its orbit around the Sun. Unlike Earth, which tilts at 23.5 degrees and gives us our seasons, Mercury tilts less than 1 degree. This minimal tilt creates something extraordinary at Mercury's poles, regions of permanent shadow. Imagine craters so deep and positioned so perfectly that sunlight has never touched their floors, not once in billions of years. These aren't just shadowy spots that get a brief respite from the sun's rays. They're cosmic refrigerators that have maintained freezing temperatures since the solar system was young. The ice hiding in these shadowed craters likely arrived as passengers on comets and asteroids that crashed into Mercury over billions of years. Each impact brought water in the form of ice, and while most of this water would have immediately vaporized in Mercury's harsh environment, some of it found its way into these permanently shadowed regions where it froze solid and has remained frozen ever since. Discovering this ice required some detective work that reads like a cosmic mystery novel. Scientists couldn't simply point a telescope at Mercury and see the ice. It's hidden in shadows deeper than the darkest caves on Earth. Instead, they used radar signals bounced off Mercury's surface from Earth-based telescopes. When these radar waves hit the ice deposits, they reflected back with a distinctive signature that told scientists they were seeing something highly reflective and consistent with water ice. Later, NASA's Messenger spacecraft provided even more compelling evidence, mapping Mercury's surface in unprecedented detail and confirming that these mysterious radar-bright regions were indeed located in areas of permanent shadow. The spacecraft's instruments detected not just ice but also organic compounds, carbon-based materials that likely arrived on the same comets that delivered the water. The amount of ice hiding in Mercury's shadows is staggering. Scientists estimate there could be between 100 billion and 1 trillion tons of water ice locked away in these polar refuges. That's enough water to fill a lake several kilometers across and hundreds of meters deep. This ice represents a record of billions of years of cometary impacts, a frozen library that preserves the early history of our solar system in Mercury's most unlikely locations. This discovery fundamentally changes how we think about water in our solar system. We used to believe that water could only exist as ice in the cold outer regions, far from the sun's intense heat. Mercury's polar ice shows us that water can survive even in the most unlikely places, protected by nothing more than permanent shadows and the cold of space. The existence of this ice also raises intriguing questions about Mercury's history and future. Could these ice deposits ever be accessed by future robotic missions? Could they tell us about the composition of the ancient comets that delivered them? Some scientists even speculate about whether these shadowed regions might harbor complex organic molecules, the building blocks of life, preserved in cosmic cold storage for billions of years. The paradox of ice on Mercury reminds us that the universe often surprises us. Here's a world where temperatures during the day can reach 430 degrees Celsius, hot enough to melt tin. Yet just a few hundred kilometers away, in craters that never see sunlight, water ice sits frozen solid at temperatures colder than Antarctica's winter. It's a reminder that even in the most extreme environments, nature finds ways to preserve the unexpected. Mercury, the speed demon of our solar system, carries its own secret ice age in the permanent shadows of its poles. Fact 5. Jupiter's moon Ganymede is bigger than Mercury. In the grand hierarchy of our solar system, we're taught to think of moons as smaller companions to planets, faithful satellites that orbit their larger hosts like cosmic children following their parents. But Jupiter's moon Ganymede breaks this comfortable assumption in the most spectacular way. Ganymede isn't just large for a moon, it's larger than Mercury, the smallest planet in our solar system. Here we have a moon that has outgrown a planet, a satellite that dwarfs one of the Sun's own children. Ganymede stretches 5,268 kilometers across, making it not just the largest moon in our solar system, but larger than Mercury by more than 400 kilometers. If Ganymede orbited the Sun instead of Jupiter, it would easily qualify as a planet in its own right. Instead, it contents itself with being the largest member of Jupiter's magnificent court of moons, a world so substantial it has earned the title of the solar system's largest satellite. But Ganymede's size is only the beginning of its remarkable story. This moon possesses something that even Mercury lacks, its own magnetic field. Most moons are magnetically quiet, protected by their parent planet's magnetic field or simply lacking the internal dynamics necessary to generate their own. Ganymede is different. Deep within its interior, this moon generates its own magnetic field, likely through the same process that tied to Earth's, a molten, electrically conducting core that moves as the world rotates. This magnetic field makes Ganymede unique among moons. It means that Ganymede has its own magnetosphere, a bubble of magnetic influence that deflects some of the charged particles streaming from the Sun and from Jupiter itself. When the Hubble Space Telescope observed auroras dancing in Ganymede's thin atmosphere, scientists realized they were witnessing something unprecedented, a moon with its own northern and southern lights, powered by its own magnetic field. The existence of this magnetic field tells us something profound about Ganymede's interior. Unlike our own moon, which is relatively cold and geologically dead inside, Ganymede must have a partially molten interior to generate its magnetic field. This suggests a world that's still dynamically active, with heat sources that keep its deep interior warm and moving. The most likely explanation is that Ganymede has a layered structure, a solid inner core, a liquid iron outer core, and a rocky mantle, much like Earth but on a smaller scale. But perhaps most intriguingly, Ganymede likely harbors more water than all of Earth's oceans combined. Beneath its icy surface lies what scientists believe to be a subsurface ocean, a vast body of liquid water sandwiched between layers of ice. This ocean could be 100 kilometers deep, 10 times deeper than Earth's deepest ocean trenches. The water stays liquid due to the gravitational flexing caused by Jupiter's immense gravity and the gravitational tugs from Ganymede's fellow moons, creating enough heat through tidal forces to prevent the ocean from freezing solid. The surface of Ganymede tells a story written in ice and rock, divided into two distinct types of terrain. Dark regions, among the oldest surfaces in the solar system, are heavily cratered and tell of billions of years of bombardment by asteroids and comets. Lighter regions show evidence of more recent geological activity. Groove terrain that suggests Ganymede's surface has been stretched and reformed by internal forces. This moon has a complex geological history that rivals that of many planets. From Jupiter's cloud tops, Ganymede would appear as a substantial world, not just a tiny point of light like most moons appear from their parent planets. Its size means it exerts significant gravitational influence on Jupiter's other moons, participating in a complex orbital dance that includes Europa and Io in what's called a Laplace resonance, a gravitational relationship that keeps these moons locked in a precise mathematical rhythm. If we could somehow visit Ganymede, we'd find a world of striking contrasts. The gravity would be about 14% of Earth's, enough to keep you firmly planted, but light enough to make walking feel bouncy and dreamlike. The thin atmosphere would be unbreathable, composed mainly of oxygen created when Jupiter's radiation splits water molecules on the surface. Above, Jupiter would dominate the sky, appearing 11 times larger than our moon appears from Earth. Ganymede reminds us that our solar system doesn't always follow the simple rules we learnt in school. Here's a moon that outgrew a planet, a satellite with its own magnetic field, a world that might harbor an ocean larger than Earth's. In the cosmic dance around Jupiter, size doesn't always determine status. Fakey Fact 6. Earth's atmosphere was formed by ancient bacteria. Take a deep breath, feel that oxygen filling your lungs, that life-giving gas that makes every heartbeat possible. Now imagine a time when Earth's atmosphere contained virtually no oxygen at all, when breathing as we know it would have been impossible, when our planet's sky held a completely different mixture of gases. The oxygen you're breathing right now isn't a natural feature of rocky planets. It's a gift from ancient bacteria, microscopic organisms that fundamentally transformed our world billions of years ago and made complex life as we know it possible. Early Earth was a very different world from the one we inhabit today. About 4 billion years ago, our planet's atmosphere was dominated by methane, ammonia, hydrogen and other gases that would be toxic to most life forms we're familiar with. There was virtually no free oxygen in the atmosphere, perhaps less than 1% of current levels. This wasn't unusual. Most rocky planets have atmospheres dominated by carbon dioxide and other gases. What happened next on Earth was extraordinary, and as far as we know, unique in our solar system. The transformation began with tiny single-celled organisms called cyanobacteria, also known as blue-green algae. These microscopic pioneers developed something revolutionary: the ability to use sunlight to convert carbon dioxide and water into food, releasing oxygen as a waste product. This process, which we now call photosynthesis, was initially just a clever way for these bacteria to make a living. They had no idea they were about to change the world. At first, the oxygen produced by these ancient bacteria didn't accumulate in the atmosphere. Earth's early oceans contained dissolved iron, and oxygen readily combined with this iron to form rust-colored iron oxide that settled to the bottom of the seas. For hundreds of millions of years, the oxygen from cyanobacteria was essentially absorbed by the oceans, creating distinctive red-banded iron formations that geologists can still see in ancient rocks today. These geological layers are like pages in Earth's diary, recording the gradual buildup of oxygen in our planet's early history. But eventually, around 2.5 billion years ago, something dramatic happened. The oceans became saturated with iron oxide, meaning they couldn't absorb any more oxygen. Suddenly, oxygen began accumulating in the atmosphere in what scientists call the Great Oxidation Event. This wasn't a gentle transition. It was one of the most dramatic changes in Earth's history, fundamentally altering the chemical composition of our planet's atmosphere. This atmospheric transformation was initially catastrophic for most existing life forms. Many of the organisms that had thrived in Earth's oxygen-free environment found the gas toxic. Oxygen is highly reactive and can damage cellular structures if organisms aren't adapted to handle it. The Great Oxidation Event likely caused the first mass extinction in Earth's history, wiping out countless species that couldn't adapt to the new oxygen-rich environment. However, this atmospheric revolution also opened the door for new forms of life. Oxygen is an incredibly efficient fuel for cellular processes. Organisms that could harness oxygen for metabolism could extract far more energy from food than their oxygen-free ancestors. This set the stage for the evolution of more complex life forms, first more sophisticated single-celled organisms, then eventually multicellular life, and ultimately the rich diversity of plants and animals we see today. The impact of ancient bacteria on our atmosphere extends beyond just oxygen. These early photosynthetic organisms also began removing carbon dioxide from the atmosphere, helping to moderate Earth's climate. Without this bacterial intervention, Earth might have experienced a runaway greenhouse effect, similar to what we see on Venus today. Instead, the gradual removal of carbon dioxide and addition of oxygen helped create a more stable climate suitable for complex life. Even today, billions of years later, Earth's atmosphere continues to be actively maintained by living organisms. Plants, algae, and cyanobacteria still produce most of our oxygen through photosynthesis, while animals and other organisms consume it through respiration. It's a delicate balance that has been maintained for billions of years, a testament to the power of life to transform planetary environments. When you step outside and breathe fresh air, you're participating in a process that began with ancient bacteria billions of years ago. Every breath connects you to the earliest life forms on Earth, those microscopic pioneers who accidentally terraformed our planet. The oxygen in our atmosphere isn't just a fortunate accident. It's the legacy of countless generations of tiny organisms that changed the world simply by trying to survive. In a very real sense, we owe our existence to ancient bacteria that transformed poison into the breath of life. Fact 7. Mars has the largest volcano in the solar system. Imagine standing at the base of the tallest mountain you've ever seen, craning your neck back until it aches, trying to glimpse the summit disappearing into clouds far above. Now imagine that mountain is not just tall, but so vast that you could walk for days along its base and never see where it ends. This is Olympus Mons on Mars. Not just the largest volcano in our solar system, but a geological giant so enormous it challenges our understanding of what mountains can be. Olympus Mons towers nearly 22 kilometers above the Martian plains, making it almost 3 times taller than Mount Everest. But its height is only part of the story. This colossal volcano stretches roughly 600 kilometers across its base, wider than the entire state of Arizona. If you could somehow transport Olympus Mons to Earth and set it down in France, it would cover most of the country. Its slopes are so gentle that if you were climbing it, you might not even realize you were ascending a mountain until you looked back and saw how far above the surrounding landscape you'd climbed. The sheer scale of Olympus Mons seems to mock the mountains we know on Earth. Our tallest peaks, impressive as they are, would be lost in the foothills of this Martian giant. The volcano's summit, caldera, the collapsed crater at its peak, is roughly 85 kilometers across and contains multiple overlapping craters that tell the story of countless eruptions spanning millions of years. Standing on the rim of this caldera would be like looking across a circular valley wider than many Earth cities. But how does a mountain grow so impossibly large? The answer lies in the fundamental differences between Mars and Earth. On our planet, the constant movement of tectonic plates means that volcanoes rarely stay in one place long enough to build truly enormous structures. As the plates drift, they carry volcanoes away from their underlying hotspots, creating chains of smaller mountains rather than single massive peaks. Think of the Hawaiian island chain, where the moving Pacific plate has created a series of volcanoes as it drifts over a stationary hotspot beneath. Mars, however, tells a different story. The red planet lacks the active plate tectonics that constantly reshape Earth's surface. When a hot spot of magma found its way to the Martian surface billions of years ago, it stayed put for millions upon millions of years. Eruption after eruption built layer upon layer of hardened lava, slowly constructing a mountain of almost incomprehensible size. It's as if nature conducted an experiment. What happens when you let a volcano grow without interruption for geological ages? The result is a mountain so large it creates its own weather patterns. Olympus Mons is so tall that its peak extends well into Mars's thin atmosphere. Clouds often form around its summit, and the mountain can influence wind patterns across vast regions of Mars. From orbit, astronauts would see this massive volcano as a distinctive feature dominating an entire hemisphere of the planet. The slopes of Olympus Mons are surprisingly gentle, typically rising at angles of only 2 to 5 degrees. This gradual incline exists because the lava that built the mountain was relatively fluid, flowing great distances before cooling and hardening. Walking up these slopes would be like hiking up a very long, very gradual hill, rather than scaling a steep mountain face. The gentle gradient means that the summit, despite being 22 kilometers high, wouldn't provide the dramatic cliff-like views we might expect from such an enormous mountain. Scientists believe Olympus Mons was likely active as recently as 25 million years ago, practically yesterday in geological terms. This suggests that Mars may not be the geologically dead world we once thought. Deep beneath the planet's surface, heat sources might still exist, waiting for the right conditions to once again send magma flowing up through the mountain's ancient channels. From Earth, when we look up at Mars as a reddish dot in our night sky, it's humbling to think that tiny point of light hosts a mountain that dwarfs anything on our planet. Olympus Mons represents the kind of geological grandeur that's possible when a world has the time and stability to build truly massive structures. It reminds us that Mars, despite appearing barren and lifeless from our perspective, was once a dynamic world capable of creating wonders that surpass anything in our earthly experience. Standing on Mars and gazing up at Olympus Mons would be like witnessing geology taken to its absolute extreme. A mountain that pushes the very limits of what's possible when rock and time conspire to build monuments to planetary forces. Fact 8. Saturn would float in water. Here's a thought experiment that sounds like it belongs in a cosmic comedy. Imagine you could build a bathtub large enough to hold Saturn, that magnificent ringed giant that graces our outer solar system. Fill that impossible bathtub with water, and something magical would happen. Saturn would float. This isn't poetic metaphor or wishful thinking. It's a consequence of fundamental physics that reveals just how unusual this beautiful planet really is. Saturn's average density is only about 7/10 that of water. While water has a density of 1 gram per cubic centimeter, Saturn averages just 0.69 grams per cubic centimeter. This makes Saturn the least dense planet in our solar system, so light that it would bob on the surface of a cosmic ocean like the world's most spectacular beach ball. The image seems almost absurd, a planet famous for its majestic rings, larger than Earth could ever dream of being, yet light enough to float. To understand how a world so enormous can be so light, we need to peer beneath Saturn's swirling cloud tops and explore what this giant is actually made of. Saturn is what astronomers call a gas giant, though that term is somewhat misleading. It's not a ball of gas floating in space, but rather a world composed primarily of hydrogen and helium, the lightest elements in the universe. These gases become increasingly compressed towards Saturn's center, eventually becoming liquid, and then metallic under the immense pressure. But they never become as dense as the rock and metal that make up planets like Earth. Picture Saturn as a cosmic onion with layers of increasingly dense material toward its core. The outermost layer consists of hydrogen and helium gas that we see as swirling clouds and bands of color. Deeper down, the pressure increases until these gases become liquid hydrogen and helium. Deeper still, under pressures millions of times greater than Earth's atmosphere, hydrogen enters an exotic state called metallic hydrogen, where it behaves more like a liquid metal than the gas we're familiar with. At Saturn's very center there's likely a core of rock and ice, but even this solid core is relatively small compared to the planet's overall size. This layered structure means that Saturn's mass is distributed very differently from terrestrial planets. On Earth, dense iron and nickel are concentrated in our planet's core, giving us a relatively high overall density. Saturn's core, while possibly containing some rock and metal, makes up only a small fraction of the planet's total mass. Most of Saturn consists of light hydrogen and helium, which keeps the overall density remarkably low. The implications of Saturn's low density extend beyond just this amusing flotation fact. This lightness affects how Saturn behaves as a world. The planet rotates rapidly, completing one day in just 10.5 hours. This fast rotation, combined with Saturn's low density and gaseous composition, causes the planet to bulge significantly at its equator. Saturn is noticeably flattened, about 10% wider at its equator than from pole to pole. If Saturn was spinning much faster, it might literally fly apart, unable to hold itself together against the centrifugal forces. Saturn's low density also influences its magnificent ring system. The planet's relatively weak gravity, spread over such a large volume, creates complex dynamics that help maintain the intricate structure of its rings. The interplay between Saturn's gravity, the gravity of its many moons, and the countless particles that make up the rings, creates the detailed patterns and gaps we see in those beautiful bands of ice and rock. This floating giant also generates its own heat, radiating about 2.5 times more energy than it receives from the sun. This internal heat source comes from the slow gravitational compression of the planet. Saturn is still slowly shrinking and converting gravitational potential energy into heat, a process left over from its formation 4.5 billion years ago. This internal warmth, combined with Saturn's rapid rotation and low density, drives the powerful winds and storm systems we observe in its atmosphere. When we look up at Saturn through a telescope and marvel at its rings, we're seeing a world that defies our earthbound intuition about what planets should be like. Here's a giant that could float in water, a world made mostly of the same stuff that fills party balloons, yet massive enough to hold over 60 moons in its gravitational embrace. Saturn reminds us that planets can be far stranger and more wonderful than our everyday experience suggests. Cosmic paradoxes that float through space, light as gas, yet mighty enough to reshape the architecture of our solar system. Fact 9. Neptune's winds are the fastest in the solar system. In the frozen reaches of our solar system, nearly 3 billion miles from the sun's warming rays, lies Neptune, a world wrapped in perpetual twilight, where winds race across ice-blue clouds at speeds that would make Earth's most violent hurricanes seem like gentle breezes. Here, in this distant realm where sunlight arrives 900 times weaker than it reaches Earth, nature has crafted the most ferocious winds in our solar system, screaming across Neptune's atmosphere at over 2,000 kilometers per hour, faster than the speed of sound on Earth. These supersonic winds present one of the most puzzling mysteries in planetary science. Logic suggests that worlds farther from the sun should be calmer, more sedate places, where the lack of solar energy would create relatively peaceful atmospheres. After all, it's the sun's heat that drives most weather systems we're familiar with. On Earth, solar energy evaporates water, creates temperature differences, and powers the winds that shape our climate. So how does Neptune, receiving so little solar energy, generate winds that are faster than anything else in our solar system? The answer lies in Neptune's internal heat source. Like its neighbor Uranus, Neptune generates more energy than it receives from the Sun, about 2.5 times more. This internal heat comes from the planet's formation, when gravitational energy was converted to thermal energy as countless particles crashed together to build the world. Unlike other planets that have largely radiated away this primordial heat, Neptune still glows with warmth from its birth 4.5 billion years ago. This internal furnace provides the energy that drives those incredible winds, but internal heat alone isn't enough to explain Neptune's wind speeds. Scientists believe the key lies in the planet's unique atmospheric dynamics. Neptune's atmosphere consists primarily of hydrogen and helium, with traces of methane that give the planet its distinctive blue color. This methane absorbs red light from the sun, leaving behind the blue wavelength that we see. But more importantly, the atmospheric composition and structure create conditions perfect for generating extreme winds. The winds on Neptune aren't evenly distributed. The fastest winds blow in the opposite direction to the planet's rotation, creating jet streams that race around the planet like cosmic race cars on an atmospheric highway. These retrograde winds are concentrated in bands, similar to Jupiter's more famous bands but moving at much higher speeds. The contrast between these high-speed jets and calmer regions creates shear forces that help maintain and accelerate the wind systems. Perhaps most remarkably, Neptune's winds appear to be getting faster. When Voyager 2 flew past Neptune in 1989, it measured wind speeds of about 2,000 kilometers per hour. More recent observations using the Hubble Space Telescope suggest that these winds have increased in speed, reaching nearly 2,500 kilometers per hour in some regions. This acceleration over just a few decades hints at dynamic processes we don't yet fully understand. The most famous manifestation of Neptune's violent weather is the Great Dark Spot, a massive storm system comparable in size to Jupiter's Great Red Spot. This oval-shaped storm, first observed by Voyager 2, was racing across Neptune's atmosphere with winds reaching 2,400 kilometers per hour. However, when Hubble looked for the Great Dark Spot a few years later, it had vanished, replaced by new storm systems in different parts of the planet. Unlike Jupiter's centuries-old Great Red Spot, Neptune's storms appear and disappear over much shorter timescales, suggesting a more dynamic and chaotic atmospheric system. These extreme winds exist in an environment that would be unimaginably hostile to any form of life we know. Temperatures at Neptune's cloud tops plunge to -218 degrees Celsius, cold enough to freeze nitrogen solid. The atmospheric pressure increases dramatically with depth, eventually reaching levels that would crush any spacecraft we could build. Yet within this harsh environment, winds race at speeds that approach the theoretical limits of what's possible in a planetary atmosphere. From Earth, Neptune appears as a tiny blue dot, betraying no hint of the atmospheric violence raging in its distant skies. When we look at this remote world through telescopes, we're seeing the result of forces that dwarf anything in our terrestrial experience. Neptune's winds remind us that our solar system contains phenomena that push the very limits of what's physically possible, creating beauty and terror in equal measure in the cold depths of space. Fact 10. There are more moons than planets. When we first learn about our solar system as children, we're taught to count planets. 8 worlds orbiting our sun in a cosmic dance that's remained relatively unchanged for billions of years. But if we shift our attention from the primary performers to their supporting cast, we discover something remarkable. Our solar system is absolutely teeming with moons. As of our current count, over 290 confirmed moons orbit the planets in our solar system, and that number grows almost every year as our telescopes and spacecraft reveal new tiny worlds we never knew existed. This abundance of moons tells us something profound about how our solar system formed and evolved. Each moon represents a story. Some are captured asteroids that wandered too close to their host planets. Others formed alongside their planets from the same disk of material, and still others were born from cosmic collisions that scattered debris into orbit. Every moon is a world unto itself, with its own unique characteristics, history, and mysteries waiting to be explored. Jupiter alone hosts at least 95 confirmed moons, making it the center of what amounts to a miniature solar system. The 4 largest are Europa, Ganymede, and Callisto, discovered by Galileo over 400 years ago, are substantial worlds in their own right. But beyond these famous Galilean moons lie dozens of smaller satellites, many of them irregularly shaped chunks of rock and ice that were likely captured from the asteroid belt or the Kuiper belt. Some of these tiny moons are only a few kilometers across, little more than boulders held in Jupiter's gravitational embrace. Saturn, not to be outdone, claims at least 146 moons of its own. Beyond the well-known Titan with its thick atmosphere and methane lakes, Saturn's collection includes shepherd moons that help maintain the structure of its rings, co-orbital moons that share the same orbital path, and tiny moonlets embedded within the rings themselves. Some of Saturn's moons are so small they were only discovered when spacecraft flew close enough to spot them hiding among the ring particles. Even the smaller planets contribute to this moon census. Mars has its two tiny companions, Phobos and Deimos, which are probably captured asteroids shaped like potatoes. These moons are so small that if you could somehow stand on Phobos, you could literally throw a baseball hard enough to put it into orbit around the moon, or even throw it hard enough to escape Phobos entirely and send it floating off into space. Uranus and Neptune each host their own collections of moons, many of which orbit in unusual ways that tell stories of cosmic violence and capture. Uranus's moon Miranda looks like it was shattered and then reassembled, creating a patchwork surface of different terrain types. Neptune's largest moon, Triton, orbits backwards compared to the planet's rotation, strongly suggesting it was once a dwarf planet like Pluto that was captured by Neptune's gravity and forced into an orbital dance it never chose. The discovery of new moons continues at an accelerating pace. Advanced telescopes and sophisticated image processing techniques allow astronomers to spot increasingly tiny objects orbiting the giant planets. Some of these newly discovered moons are only a few hundred meters across, essentially large boulders that happen to be orbiting planets instead of tumbling through space as asteroids. This proliferation of moons has practical implications for our understanding of planetary formation. Each moon provides clues about the conditions that existed when our solar system was young. The composition, orbital characteristics, and physical properties of these moons help scientists reconstruct the chaotic early period when planets were still growing and the solar system was filled with debris from its formation. The sheer number of moons also highlights the dynamic nature of our solar system. Moons can be created through collisions, captured from passing objects, or even destroyed by tidal forces if they venture too close to their host planets. Some moons may be temporary visitors destined to either crash into their planets or escape into independent orbits around the Sun. Perhaps most remarkably, many of these moons might harbor conditions suitable for life. Europa's subsurface ocean, Enceladus's warm geysers, and Titan's complex organic chemistry all suggest that the search for life in our solar system should focus as much on moons as on planets. In this census of worlds, the supporters may prove more interesting than the stars they orbit, reminding us that in our solar system, the supporting cast vastly outnumbers the main characters. Fact 11. Pluto has a heart-shaped glacier. In the far reaches of our solar system, where sunlight arrives as barely more than a bright star in an eternally dark sky, orbits a small world that captured human imagination for decades. Pluto, the distant dwarf planet that once held the title of our solar system's ninth planet, seemed destined to remain forever mysterious, until NASA's New Horizons spacecraft flew past in 2015 and revealed something extraordinary. There, prominently displayed across Pluto's surface, like a cosmic valentine, lies a heart-shaped glacier that transforms our understanding of this distant world from a cold, lifeless rock into a place of surprising beauty and dynamic geology. This heart-shaped feature, formerly named Toumbour Regio, after Pluto's discoverer Clyde Toumbour, spans roughly 1,600 kilometers across, larger than Texas and Oklahoma combined. But this isn't just a static geological formation frozen in time. This heart is alive with activity, constantly reshaping itself through processes that shouldn't exist on such a small, distant world. The heart consists primarily of nitrogen ice, along with smaller amounts of methane and carbon monoxide ices, creating a glacier that flows and moves despite temperatures that hover around -230 degrees Celsius. The existence of active geology on Pluto came as a complete surprise to planetary scientists. Conventional wisdom suggested that a world so small and so far from the Sun should be geologically dead, its surface unchanged for billions of years except for the occasional impact crater. Pluto has only about 2/3 the diameter of our Moon and receives less than 1% of the sunlight that reaches Earth. By all rights, it should be a frozen, inactive ball of rock and ice drifting silently through the outer darkness. Instead, New Horizons revealed a world where nitrogen ice sublimates from solid directly to gas in some regions, then condenses back to solid in others, creating a slow but continuous cycle of glacial movement. The heart-shaped glacier acts like a massive, slow-motion weather system, with winds of flowing ice carrying material across hundreds of kilometers over thousands of years. This nitrogen ice is remarkably soft at Pluto's temperatures, flowing like very thick honey, and constantly resurfacing parts of the planet. The heart's left lobe, known as Sputnik Planitia, sits within what appears to be an ancient impact basin, a massive crater created when some cosmic projectiles slammed into Pluto eons ago. This depression has become a reservoir for nitrogen ice that flows in from surrounding highlands, creating convection cells that churn the ice in patterns that can be seen from space. These convection cells, each roughly 20 to 30 kilometers across, create a polygonal pattern that looks almost like a frozen honeycomb across the glacier's surface. What makes this heart-shaped glacier even more remarkable is its influence on Pluto's orientation in space. The concentration of nitrogen ice creates a mass imbalance that has actually caused Pluto to roll over time, reorienting itself so that the heart faces roughly toward Pluto's largest moon, Charon. This relationship between Pluto and Charon, locked in gravitational synchronization where the same faces always point toward each other, means that the heart is always visible from Charon's surface, like a constant reminder of cosmic affection between these two distant worlds. The heart also plays a role in Pluto's thin atmosphere. As nitrogen sublimates from the glacier's surface, it creates most of Pluto's atmospheric pressure. Fact 12. Jupiter's Great Red Spot is a centuries-old storm. Imagine a storm so vast that you could drop 2 or 3 Earths into it and still have room left over. Picture winds that have been howling continuously. Not for days or weeks, but for centuries. Possibly since before your country was founded, before your great-great-grandparents were born, before humans had any idea that other worlds even existed. This is Jupiter's Great Red Spot, a hurricane-like storm system that has been raging in the giant planet's atmosphere for at least 350 years, and possibly much longer. The Great Red Spot is more than just a weather phenomenon. It's a permanent feature of Jupiter, as much a part of the planet's character as its bands of colored clouds or its family of moons. This massive anticyclone, a high-pressure storm system that rotates counterclockwise in Jupiter's southern hemisphere, measures roughly 16,000 kilometers across at its widest point. To put that in perspective, the entire circumference of Earth is only about 40,000 kilometers. This single storm is large enough that our entire planet would be lost within its swirling winds. What makes the Great Red Spot even more remarkable is its longevity. On Earth, even the most powerful hurricanes last only days or weeks before they dissipate, their energy scattered by contact with land, cooler water, or atmospheric conditions that disrupt their circulation. But Jupiter has no solid surface to break up storms, no continents to interrupt the flow of atmospheric currents. The Great Red Spot exists in a fluid environment where, once established, a stable circulation pattern can persist for geological ages. The storm's distinctive red color has puzzled scientists for decades. The exact chemistry responsible for this coloration remains uncertain, but it likely involves complex organic compounds created when Jupiter's atmospheric gases are exposed to solar radiation and cosmic rays. These compounds, possibly including phosphorus, sulfur, or hydrocarbon molecules, create the rust-colored appearance that makes the spot stand out against Jupiter's more muted bands of brown and tan clouds. Historical observations suggest that the Great Red Spot may be slowly changing over time. When Giovanni Cassini first documented a large spot on Jupiter in 1665, it may have been the same feature we see today, though we can't be certain. What we do know is that the spot has been continuously observed since the early 1800s. And during that time it has shown variations in size, color intensity, and position. Currently, the Great Red Spot appears to be shrinking. Measurements from the late 1800s suggested it was about 40,000 kilometers across, but recent observations show it has contracted to roughly half that size. This shrinkage raises fascinating questions about the storm's future. Will the Great Red Spot eventually disappear entirely, ending a centuries-long atmospheric phenomenon, Or will it stabilize at a smaller size and continue its eternal dance through Jupiter's clouds? Some scientists speculate that the spot goes through cycles of expansion and contraction over very long time periods, meaning what we're seeing might be a normal part of its long-term behavior. The Great Red Spot doesn't exist in isolation. It interacts dynamically with Jupiter's other atmospheric features. The planet's banded appearance comes from jet streams that circle the globe at different latitudes, and the Great Red Spot sits between two of these jet streams like a massive boulder in a river. These interactions help to maintain the spot's structure while also influencing its movement and evolution over time. The storm's winds are truly spectacular, racing around its perimeter at speeds of up to 430 kilometers per hour, faster than the strongest hurricanes ever recorded on Earth. But unlike terrestrial storms that derive their energy from warm ocean water, the Great Red Spot is powered by Jupiter's internal heat and the complex dynamics of the planet's thick atmosphere. Jupiter radiates more heat than it receives from the Sun, providing a constant energy source that can sustain atmospheric phenomena on scales impossible in our earthly experience. Recent observations from NASA's Juno spacecraft have revealed that the Great Red Spot extends much deeper into Jupiter's atmosphere than previously thought, possibly penetrating hundreds of kilometers below the visible cloud tops. This suggests that the storm is not just a surface phenomenon, but a deep-rooted feature of Jupiter's atmospheric circulation. When we look up at Jupiter in our night sky, that tiny wandering star contains within it a storm larger than our entire world, older than our oldest cities, powered by forces that dwarf anything in our terrestrial experience. The Great Red Spot reminds us that weather on other worlds can achieve a scale and permanence that makes our most dramatic storms seem like brief whispers in comparison. Back 13. There may be a hidden planet beyond Neptune. In the darkness beyond Neptune, where sunlight fades to barely more than starlight, and temperatures plunge to levels that would freeze the air we breathe, something mysterious may be lurking. Astronomers have discovered a puzzle written in the orbits of distant objects, a gravitational signature that suggests the presence of a massive world we've never seen, a hypothetical ninth planet that could be larger than Earth, hiding in the outer reaches of our solar system like a cosmic ghost. This theoretical world, dubbed Planet 9 by researchers, emerged not from direct observation but from detective work that would make Sherlock Holmes proud. As astronomers mapped the orbits of small icy objects in the Kuiper Belt, that distant region beyond Neptune populated by dwarf planets like Pluto and Eris, they noticed something strange. Several of these objects shared unusual orbital characteristics that seemed too coincidental to be random. Their orbits clustered together in space, all tilted at similar angles and elongated in the same direction, as if something massive was shepherding them into these peculiar paths. The mathematics are compelling. Computer simulations suggest that a planet with roughly 10 times the mass of Earth, orbiting the Sun at a distance of perhaps 400 to 800 times Earth's distance, could create exactly the gravitational effects astronomers observe in these distant objects. This hypothetical world would take between 10,000 and 20,000 years to complete a single orbit around the Sun, moving so slowly through its distant path that it would appear essentially motionless against the stellar background, making it incredibly difficult to spot even with our most powerful telescopes. If Planet 9 exists, it would represent a fundamentally different type of world from the planets we know. Unlike the rocky inner planets or the gas giants closer to the Sun, this distant world would likely be what astronomers call a super-Earth, larger than our planet, but smaller than Neptune. It might have a thick atmosphere and possibly even a subsurface ocean, warmed not by the Sun's feeble rays, but by the heat of its own formation, still radiating warmth into space after billions of years. The hunt for Planet 9 represents one of the greatest detective stories in modern astronomy. Multiple research teams around the world are systematically scanning the sky, looking for a slowly moving point of light that stands out against the fixed stars. This search requires extraordinary patience and precision. Planet 9, if it exists, would be incredibly faint, reflecting only a tiny fraction of the already weak sunlight that reaches its distant orbit. Finding it would be like searching for a needle in a haystack the size of the sky. Some scientists remain skeptical about Planet 9's existence, proposing alternative explanations for the strange orbital clustering. Perhaps the gravitational effects come not from a single large planet, but from a collection of smaller objects. Or maybe, Our understanding of gravity itself needs refinement at these extreme distances. The clustering could even be an observational bias. We might simply be better at finding objects in certain parts of the sky, creating an apparent pattern where none actually exists. But the Planet 9 hypothesis continues to gain support as astronomers discover more distant objects with orbits that fit the predicted pattern. Each new discovery either strengthens the case for a hidden planet, or provides new constraints that help researchers refine their models. The search has also led to unexpected discoveries. Several new dwarf planets, and dozens of previously unknown asteroids have been found in the outer solar system during the hunt for Planet 9. The existence of Planet 9 would revolutionize our understanding of how our solar system formed. Current models suggest that the outer planets migrated significantly during the solar system's early history, with Jupiter and Saturn moving outward and potentially ejecting other planets entirely. Planet 9 might be a survivor of this chaotic period, a world that was flung into the outer darkness, but managed to remain gravitationally bound to the Sun. If Planet 9 is eventually found, it would mark one of the most significant astronomical discoveries of our time, the first new planet in our solar system since Neptune was discovered in 1846. It would remind us that even our own cosmic neighborhood still holds major surprises, that worlds we've never imagined might be orbiting silently in the darkness beyond our current knowledge. Until then, Planet 9 remains a tantalizing mystery, a possible world that exists at the intersection of mathematics and imagination, waiting to be revealed by patient astronomers scanning the depths of space for signs of our solar system's most elusive resident. Fact 14. Uranus rotates on its side. Imagine a world where the concept of normal seasons becomes completely meaningless, where summer and winter don't alternate every few months but stretch across decades, where the sun might circle overhead for 42 Earth years before finally setting for an equally long night. This is the reality on Uranus, the ice giant that decided to lie down on the job, rotating on its side with an axial tilt of about 98 degrees, essentially rolling around the sun like a cosmic barrel instead of spinning like a top. Most planets in our solar system spin somewhat like Earth does, with their rotational axes roughly perpendicular to their orbital planes. This gives them relatively normal seasonal cycles, as different hemispheres receive varying amounts of sunlight throughout their years. Mars tilts at about 25 degrees, giving it Earth-like seasons. Even Jupiter and Saturn maintain relatively upright orientations, but Uranus breaks all the rules, tipped over so far that its axis of rotation lies almost in the plane of its orbit around the Sun. This extreme tilt creates the most bizarre seasonal pattern in our solar system. Each pole of Uranus experiences 42 years of continuous daylight, followed by 42 years of continuous darkness, as the planet completes its 84-year orbit around the Sun. During Uranus's summer solstice, one pole points directly toward the Sun, while the other pole faces away into the depths of space. The planet's equatorial regions experience something closer to normal day-night cycles, but even these are influenced by the planet's sideways orientation, creating seasonal patterns that would bewilder anyone accustomed to Earth's regular rhythm. The question of how Uranus ended up in this sideways orientation has puzzled astronomers for decades. The most widely accepted theory suggests that early in the solar system's history, when planets were still forming and space was filled with debris, Uranus suffered one or more catastrophic collisions with objects perhaps the size of Earth. These impacts were so violent that they literally knocked the planet over, changing its rotational axis from roughly vertical to nearly horizontal. Imagine a spinning top that gets hit by a baseball. The impact doesn't just change the top's position, it fundamentally alters how it spins. Alternative theories propose that Uranus's tilt developed more gradually through gravitational interactions with other planets, or through the influence of a large moon that was later destroyed or ejected from the system. Some models suggest that the combined gravitational effects of Jupiter and Saturn could have gradually tilted Uranus over millions of years, though this process would require very specific initial conditions. This sideways rotation has profound effects on Uranus's magnetic field, which doesn't align with either the planet's rotational axis or its orbital plane. Instead, the magnetic field is tilted about 60 degrees from the rotational axis and offset from the planet's center, creating a complex and dynamic magnetosphere that changes dramatically as Uranus rotates. This unusual magnetic field structure suggests that the planet's interior is also affected by its sideways orientation, possibly influencing how heat and materials circulate within the planet. The extreme tilt also affects Uranus's ring system and moons. Unlike Saturn's rings, which lie in the planet's equatorial plane. Uranus's rings are oriented almost vertically from our perspective, creating a unique geometric arrangement that changes dramatically in appearance as the planet orbits the Sun. The major moons of Uranus orbit in the planet's equatorial plane, meaning they too follow paths that seem sideways compared to most other planetary systems. Observing Uranus from Earth, we see different aspects of the planet depending on where it is in its orbit. Sometimes we view it nearly pole-on, seeing its rings as almost perfect circles around the planet. Other times we see the planet more equator-on, with the rings appearing as narrow lines extending from either side. This changing perspective has made studying Uranus challenging, as the planet presents a fundamentally different face to us across its long orbital period. The sideways rotation of Uranus serves as a dramatic reminder that planetary formation was a violent, chaotic process. In the early solar system, massive impacts were common, and the planets we see today bear the scars of this tumultuous birth. Uranus's extreme tilt tells the story of cosmic catastrophe, of forces so powerful they could knock an entire world onto its side and forever change how it experiences the passage of seasons. When we look at Uranus through a telescope, we're seeing a world that refuses to conform to our expectations, a planet that demonstrates how the architecture of worlds can be fundamentally altered by the right combination of force and circumstance, creating beauty and strangeness in equal measure. Fact 15. The Moon is slowly drifting away from Earth. Have you ever noticed how some goodbyes happen so slowly that you barely realize they're happening at all? Tonight, as you settle into the gentle embrace of sleep, let me tell you about the most patient farewell in our solar system, the goodbye that's been unfolding for billions of years right above our heads. The Moon is slowly drifting away from Earth, about 3.8 centimeters per year. That's roughly the same distance your fingernails grow in a year, or about the width of a large button. It seems impossibly small, doesn't it? Yet this tiny annual journey tells one of the most beautiful stories our universe has to offer. Imagine you're holding a yo-yo, spinning it gently on its string. As it spins, the string gradually unwinds, letting the yo-yo drift farther and farther from your hand. The Moon and Earth are locked in a similar dance, but instead of string, it's gravity that connects them. And instead of unwinding quickly, this cosmic yo-yo has been slowly, patiently extending its reach for over 4 billion years. But here's where the story becomes almost magical. This gentle separation once made our skies far more dramatic than anything we see today. Picture this. Millions of years ago, when the Moon hung closer to us, solar eclipses were not just more frequent, they were spectacular cosmic theater. The Moon appeared larger in our sky, sometimes seeming to take up nearly twice the space it does now. When it passed between Earth and the Sun, the eclipse would last longer, the darkness would be deeper, and the Sun's corona would blaze around the Moon's edges like a celestial crown of fire. Ancient creatures, long before humans walked the Earth, witnessed eclipses that would leave us breathless with wonder. The Moon's shadow would sweep across prehistoric landscapes, turning midday into twilight, making stars visible in what should have been afternoon, creating moments when time itself seemed to pause. And it wasn't just the eclipses that were different. The tides were more dramatic too, surging higher up onto ancient shores, retreating farther out to sea. Picture vast tidal pools, exposed for hours longer than they are today, teeming with early life forms that evolved to the rhythm of these stronger lunar pulls. The Moon's closer presence shaped not just our coastlines, but the very evolution of life itself, creating tidal rhythms that still pulse through our bodies today. But what's truly remarkable is that this isn't a story of loss, it's a story of growing up. Think of the Moon like a child who starts by holding tightly to your hand, then gradually learns to walk beside you, then eventually strides confidently on their own path. The Moon isn't abandoning us. It's finding its own space while still remaining connected to us through gravity's invisible thread. Even now, as it drifts slowly away, the Moon continues to be our faithful companion. It still pulls our oceans in their eternal dance, still stabilizes our planet's gentle wobble, still lights our nights with the Sun's reflected glory. The relationship isn't ending, it's simply evolving. Scientists tell us that billions of years from now, the Moon will appear so small in our sky that total solar eclipses will become impossible. But that's so far in the future that entire mountain ranges will rise and crumble, continents will drift to completely new positions, and our Sun itself will have transformed into something unrecognizable. For all the nights that matter to us, for all the generations of dreamers who will gaze upward in wonder, the Moon will still be there, just giving us all a little more room to grow. And perhaps there's something deeply comforting in this cosmic patience. this gentle reminder that some of the most profound changes happen so slowly, so gradually, that we can simply rest in the knowledge that tonight, tomorrow night, and for countless nights to come, the moon will still be there, watching over us as we sleep, pulling our dreams like tides toward distant shores of possibility. Fact 16. Comets are cosmic time capsules. Close your eyes and imagine you could hold a piece of the very beginning in your hands. Not just the beginning of your life or your family's story, but the beginning of everything around us. The planets, the sun, the space between stars. Tonight, as you drift towards sleep, let me tell you about the universe's most ancient messengers, traveling through the darkness with secrets that are 4.6 billion years old. Comets are cosmic time capsules, preserving ingredients from the birth of our solar system like libraries written in ice and dust. Picture this. Before there were planets, before there was an Earth to call home, before there was even a sun to warm us, there was a vast, swirling cloud of gas and dust floating in the cosmic dark. It was cold out there, so cold that water froze instantly, so cold that gases became solid, so cold that time itself seemed to move slowly. In this ancient nursery, tiny particles began to stick together, like snowflakes gathering on a winter morning, building slowly into chunks of ice mixed with rock and organic compounds, the raw materials of worlds yet to be born. Most of this primordial material was swept up as the sun ignited and the planets formed, transformed by heat and pressure into the familiar worlds we know today. But some pieces, the lucky few, were flung so far from the sun's warming influence that they remained frozen unchanged, like photographs of that first cosmic winter. These became our comets, patient time travelers carrying messages from an era when everything was possible and nothing yet existed. When we see a comet blazing across our night sky, tail streaming behind it like a celestial wedding veil, we're not just watching a pretty light show, we're witnessing something extraordinary. We're seeing the solar system's baby pictures being delivered to us across the darkness. That glowing tail isn't just ice turning to vapor, it's literally the stuff from which everything around us was made, the same materials that became the water in our oceans, the carbon in our bodies, the oxygen we breathe. Think of comets like ancient recipe cards, preserved in the universe's deepest freezer, while the ingredients here on Earth have been mixed and remixed, cooked and seasoned by billions of years of geological activity. Comets have kept the original recipe intact. When scientists study a comet, they're reading the universe's cookbook, discovering what flavors were available when our cosmic meal was first being prepared. Some of these wandering time capsules take hundreds, even thousands of years to complete a single orbit around the sun. Imagine a comet that appeared in the sky when your great-great-great-grandmother was young is only now returning, carrying the same ancient ice, the same primordial dust, the same molecular memories of that first cosmic dawn. It's been waiting patiently in the cold outer reaches of our solar system, like a letter written long ago, finally ready to be delivered. And here's something almost magical to consider as you settle into sleep. The water that might soothe your throat tomorrow, the breath you're breathing right now, the calcium in your bones and the iron in your blood. Some of these very atoms may have once traveled through space, locked in a comet's icy heart. You are not separate from these cosmic messengers. You are made of the same star stuff, the same ancient materials, the same building blocks that have been recycling through the universe for billions of years. When you dream tonight, you might dream of ice and starlight, of patient journeys through the dark, of messages written in a language older than words. And in the morning, when you wake and step outside, if you happen to see a comet's faint trail across the dawn sky, you'll know you're not just watching a distant visitor, you're seeing a piece of home, returning after an impossibly long journey, carrying stories of where we all came from, written in the universe's own ancient handwriting. Fact 17. Saturn's rings are shockingly young. Sometimes the most beautiful things in life are also the most temporary, and tonight as you prepare for peaceful sleep, let me share with you one of the cosmos's most surprising secrets about beauty, time, and the fleeting nature of even the grandest spectacles in our universe. Saturn's rings, those magnificent bands of ice and rock that have captivated humans since Galileo first glimpsed them through his telescope, are shockingly young, possibly only 100 million years old. In cosmic terms, that makes them practically newborns, and even more remarkably, they may vanish entirely in just a few 100 million years more. To understand just how astonishing this is, imagine that the entire history of our solar system is compressed into a single year. The sun ignited on January 1st. The planets formed by early February, and life began stirring in Earth's oceans sometime in March. Dinosaurs wouldn't appear until mid-December, and human civilization would occupy only the final few seconds before midnight on New Year's Eve. In this cosmic calendar, Saturn's rings didn't appear until sometime in late November. They're practically yesterday's news. This discovery stunned astronomers like finding out that the Grand Canyon was carved last week, or that the pyramids were built this morning. For decades, scientists assumed Saturn's rings were ancient, formed alongside the planet itself 4.6 billion years ago. They seemed so permanent, so established, like cosmic architecture that had always been. Think of it like kneading bread dough, but on a planetary scale. Every hour and 42 minutes, Iter completes another orbit around Jupiter, and with each orbit, tidal forces knead its rocky interior, generating heat through friction. It's the same principle that makes your hands warm when you rub them together, but amplified to the point where entire mountain ranges melt and reform, where lakes of liquid sulfur bubble and splash under alien skies. The result is a world that's essentially turning itself inside out, constantly. The surface of Io is younger than a human lifetime. Every few years, volcanic activity is buried or transformed every square meter of the moon's face. If you could somehow stand on Io and watch patiently, you'd see the landscape changing before your eyes. New mountains being born, while old ones dissolve back into the molten sea beneath. And the colors? Oh, the colors of this tortured paradise are like nothing else in our solar system. The sulfur compounds create a palette that looks like it was painted by an artist who had access to every warm color imaginable, but had never heard of blue or green. Yellow sulfur plains stretch toward orange horizons, punctuated by red volcanic vents, and white patches of sulfur dioxide frost. It's like looking at a world made entirely of autumn leaves and campfire flames. But perhaps most remarkably, this volcanic violence is what keeps Io's thin atmosphere alive. Each eruption doesn't just reshape the surface, it exhales gases into space, creating a tenuous atmosphere of sulfur dioxide that gets stripped away by Jupiter's powerful magnetic field, only to be constantly replenished by the next volcanic breath. Io is literally breathing through its volcanoes, exhaling its essence into the cosmic wind. From our quiet, geologically stable Earth, there's something both terrifying and beautiful about imagining such a restless world. Io reminds us that planetary surfaces don't have to be permanent, that worlds can be works of art in constant motion, sculptures that never hold the same shape twice. It's a moon that refuses to sleep, refuses to settle into quiet old age, choosing instead to burn bright and reshape itself with every passing day. As you close your eyes tonight, safe in the stillness of your own world, you might dream of distant orange skies and fountains of fire reaching toward the stars. And maybe there's something comforting in knowing that somewhere out there, orbiting the largest planet in our solar system, there's a little moon that's very much alive, painting itself in new colors every day, reminding the universe that beauty and chaos can dance together in perfect, eternal harmony. Factor 19. Neptune was discovered using math, not a telescope. Close your eyes and imagine trying to find something you've never seen, in a place you've never been, using only the whispers of its influence on things far away. Tonight, as mathematics and dreams weave together in your mind, let me tell you one of the most elegant detective stories in the history of human curiosity. The story of how we found an entire world using nothing more than pencil, paper, and the patient logic of numbers. Neptune was discovered using math, not a telescope, found through the gravitational poetry it wrote in the wandering path of distant Uranus. Picture the scene. It's the early 1800s, and astronomers have been carefully tracking Uranus, that pale blue-green world discovered by William Herschel decades earlier. They plot its position night after night, year after year, expecting it to follow the precise orbital path predicted by Newton's laws of gravity. But slowly, almost imperceptibly, they begin to notice that Uranus is misbehaving. It's wandering slightly off course, speeding up when it should slow down, slowing down when it should speed up, like a planet with a mind of its own. For years, this cosmic mystery puzzled the greatest minds of the time. Was Newton wrong? Were the laws of gravity different in the outer reaches of the solar system? Or was something else going on? Something they couldn't yet see. Then came the moment of mathematical brilliance. Two mathematicians, working independently on opposite sides of the English Channel, had the same extraordinary idea. What if Uranus wasn't misbehaving at all? What if it was simply responding to the gravitational pull of another world, an undiscovered planet lurking in the darkness beyond? Urbain Le Verrier, in France, and John Couch-Adams in England, began one of the most ambitious mathematical treasure hunts in history. Using only the subtle deviations in Uranus's path, they worked backward through the equations of celestial mechanics, essentially asking the universe, if there's a planet out there pulling on Uranus, where must it be, how massive must it be, and how fast must it be moving? Imagine the elegance of this cosmic detective work. They had no photograph of their quarry, no direct observation, no physical evidence, except for the gentle influence it exerted across billions of kilometers of empty space, yet they could calculate its position as precisely as if they were tracking a ship by its wake, finding a world by the mathematical shadow it cast on its neighbor. Le Verrier's calculations were so precise that when he sent his predictions to Johann Galler at the Berlin Observatory, the German astronomer found Neptune within 1 degree of where the mathematics said it should be. On the very first night of search, it was like calling out coordinates in the dark and having someone immediately respond, "Yes, I'm right here." This discovery represented something profound about the nature of reality itself. It suggested that the universe operates according to mathematical principles, so reliable that you can use them to find entire worlds you've never seen. It was proof that the same laws governing the fall of an apple also choreograph the dance of planets, billions of kilometers away, that mathematics isn't just human invention but a fundamental language of the cosmos itself. Think about the patience this required. These mathematicians spent months working through calculations by hand, solving equations that would challenge modern computers, all based on the faith that numbers could reveal truth across the vast emptiness of space. They were essentially listening to the gravitational whispers of an invisible world, translating subtle perturbations in one planet's orbit into the position, mass, and motion of another. And Neptune, when finally seen through telescopes, proved to be even more magnificent than the mathematics had imagined. A blue giant world, 4 times the diameter of Earth, wrapped in methane clouds and hydrogen storms, orbiting so far from the Sun that a single year there lasts 165 Earth years. It was a world of such distant beauty that sunlight, racing across space at 300,000 kilometers per second, takes over 4 hours to reach its cloud-covered surface. The discovery of Neptune marked a turning point in human understanding, the moment when we realized that our mathematical tools could extend our senses beyond what eyes could see, that we could explore the universe not just with telescopes and spacecraft, but with the pure power of logical thought. It showed us that sometimes the most profound discoveries come not from looking harder, but from thinking more carefully about what we're already seeing. As you drift towards sleep tonight, let this story remind you that there are hidden worlds everywhere, waiting to be discovered not necessarily through grand adventures or expensive equipment, but through careful attention to the subtle influences that shape everything around us. Sometimes the most distant truths reveal themselves through the gentlest whispers, and sometimes the greatest discoveries begin with simply noticing that something isn't quite where it's supposed to be, and having the curiosity to ask why. Fact 20. The asteroid belt isn't crowded. Tonight, as you settle into the gentle embrace of sleep, let me dispel one of Hollywood's most persistent myths and replace it with something far more beautiful and mysterious: the truth about the vast, lonely spaces between worlds, and how emptiness itself can be one of the universe's most elegant designs. The asteroid belt isn't crowded at all, despite what science fiction movies would have you believe, with their dramatic scenes of spaceships weaving desperately between tumbling rocks. You could fly through the asteroid belt and never see a single asteroid with your naked eyes. It's not a cosmic obstacle course. It's more like a whisper of stones scattered across an ocean of darkness, so vast that even these scattered remnants of planetary formation seem like distant islands in an infinite sea. Picture this. The asteroid belt stretches between Mars and Jupiter, occupying a region of space so enormous that if you could somehow gather all the asteroids together, they would form a sphere smaller than our moon. Imagine taking all the pebbles from a beach and scattering them across an entire continent. That's closer to the reality of our asteroid belt. The average distance between asteroids large enough to matter is measured not in kilometers, but in millions of kilometers. If you were an astronaut floating somewhere in the middle of the asteroid belt, the scene around you wouldn't be the chaotic storm of rock that movies portray. Instead, you'd find yourself surrounded by the deepest, most profound silence imaginable, with perhaps one distant speck of light, visible if you knew exactly where to look. and had a powerful telescope, the nearest asteroid might be farther away than the distance between Earth and our moon, drifting through space so slowly that you could watch it for hours and barely detect its movement. This emptiness isn't emptiness at all, though, it's spaciousness. The universe's way of giving everything room to breathe. Think of it like a cosmic garden, where the planets are flowers planted far enough apart that each can receive its full share of sunlight, with the asteroid belt serving as a gentle border between the inner garden of rocky worlds and the outer garden of gas giants. But why does Hollywood get it so wrong? Perhaps because the truth, this vast, patient emptiness, is harder to dramatize than collision and chaos. There's something almost meditative about the real asteroid belt, something that speaks to the universe's preference for harmony over drama, for space over crowding, for the elegant mathematics of orbital mechanics over random collision. The largest resident of this sparse neighborhood is Ceres, a dwarf planet so small that you could drive across it in a day, yet so significant that it contains about 1/3 of the entire asteroid belt's mass. The rest of the asteroids range from mountain-sized to pebble-sized, each following its own patient orbit around the Sun, most of them never coming close enough to another asteroid to even exchange gravitational greetings. These aren't the sharp, angular rocks of movie imagination either. Most asteroids are rounded by billions of years of micrometeorite impacts. Their surface is smooth and dark, covered in a fine dust that makes them appear almost soft in the sunlight. They're like cosmic riverstones, polished by time and the gentle touches of space weathering. Some asteroids are actually quite beautiful. Vesta has a surface marked by ancient lava flows and a mountain taller than Olympus Mons on Mars. Others contain precious metals in concentrations that would make them worth more than entire Earth economies. A few even have their own tiny moons, creating miniature solar systems within the larger dance of our cosmic neighborhood. And here's something wonderful to consider as you drift towards sleep. This spacious design isn't accidental. If the asteroid belt were truly crowded, if these remnants of planetary formation had been packed closely together, they might have eventually coalesced into another planet. Instead, Jupiter's massive gravitational influence stirred the region just enough to prevent such gathering, creating instead this beautiful, sparse collection of individual worlds, each maintaining its own dignity and distance. The real asteroid belt teaches us something profound about the nature of space itself, about how the universe prefers breathing room to crowding, about how even apparent emptiness can be full of meaning and purpose. It's a reminder that sometimes the most beautiful truths are found not in drama and collision, but in the quiet spaces between things, in the patient orbits that never intersect, in the cosmic courtesy that gives every object room to be itself. Fact 21. The Sun's atmosphere is hotter than its surface. Imagine standing next to a campfire on a cool evening feeling the warmth on your face. Now imagine taking a step back from the flames, expecting it to get cooler, only to discover that the air around the fire is somehow hotter than the fire itself. It sounds impossible, doesn't it? Yet tonight, as you prepare for peaceful sleep, let me share with you one of the Sun's most puzzling mysteries, a cosmic riddle that has scientists scratching their heads and marveling at how much we still don't understand about our nearest star. The Sun's atmosphere is hotter than its surface, much hotter. The surface of our Sun, called the photosphere, burns at about 5,500 degrees Celsius. That's hot enough to melt absolutely everything we know, hot enough to turn rock into vapor in an instant. But step away from that surface, into the Sun's outer atmosphere called the corona, and temperatures soar to over 1 million degrees Celsius, nearly 200 times hotter than the surface itself. It's like discovering that the air above a candle flame is somehow hotter than the flame, or that the steam rising from a cup of tea is burning hotter than the tea itself. This violation of what seems like common sense has puzzled solar physicists for decades, creating what they call the coronal heating problem, one of the most beautiful unsolved mysteries in all of astronomy. Think about this backwards logic for a moment. On Earth, when we move away from a heat source, things get cooler. Step away from a fireplace, and the air temperature drops. Move farther from the Sun, and planets get colder. This is how we expect the universe to behave, following the simple rule that heat flows from hot places to cool places, not the other way around. But the Sun's corona laughs at our earthbound expectations. This ghostly, shimmering atmosphere extends millions of kilometers into space, visible during solar eclipses as a delicate silver crown around the Sun's block disk. Ancient people saw this ethereal halo and named it corona, the Latin word for crown, never suspecting that this seemingly delicate decoration was actually a furnace hundreds of times hotter than the Sun's blazing surface. The mystery deepens when you consider that the corona is incredibly thin, so tenuous that if you could somehow survive its million-degree temperature, you could wave your hand through it and barely feel any resistance. It's thinner than the best vacuum we can create on Earth. Yet somehow this wispy, almost nothing atmosphere contains temperatures that would make the sun's surface seem cool by comparison. Scientists have proposed several elegant theories to explain this cosmic contradiction. Perhaps magnetic field lines, twisted and tangled by the sun's rotation, snap and reconnect like cosmic rubber bands, releasing enormous amounts of energy directly into the corona. Picture the sun's magnetic field as a vast, invisible web, constantly being stretched and twisted by the churning motions of solar plasma, occasionally snapping back into place with explosive force that heats the surrounding atmosphere. Or maybe the answer lies in waves, not the kind that crash on beaches, but magnetic sound waves that propagate up from the sun's surface, carrying energy like cosmic music into the corona. These waves might break like ocean swells on an invisible shore, dissipating their energy as heat in the thin upper atmosphere. Another possibility involves tiny explosions called nanoflares, microscopic solar storms that might constantly pepper the corona with bursts of energy too small to see individually, but powerful enough in aggregate to maintain those impossible temperatures. It would be like heating your house not with a single large furnace, but with millions of tiny matches striking simultaneously throughout every room. The truth is, we still don't know for certain, despite decades of study, despite spacecraft that have flown closer to the sun than ever before, despite computer models that can simulate the behavior of stellar plasma in exquisite detail. The corona keeps its secrets. It's humbling to realize that our nearest star, the source of all energy and life on Earth, still holds mysteries that challenge our understanding of basic physics. There's something almost poetic about this cosmic puzzle. The sun, which seems like such a steady, predictable presence in our daily lives, turns out to be full of surprises that remind us how much we still have to learn about the universe. Every sunrise brings us light and warmth from a star that is still, in many ways, a stranger to us. As you close your eyes tonight, warmed by blankets and surrounded by the gentle darkness of Earth's night, you might imagine the sun on the other side of the world continuing its ancient fusion dance, surrounded by that mysterious crown of impossibly hot plasma. And perhaps there's something comforting in knowing that even the most familiar things in our universe can still surprise us, still offer mysteries to solve, still remind us that reality is often more wonderful and strange than anything we could imagine. Fact 22. Mars has blue sunsets. There's something deeply moving about a sunset, isn't there? That daily moment when our sky transforms into a canvas of warm colors, when the sun paints the horizon in shades of gold and rose and deep amber. Tonight, as you settle into rest, let me take you on a journey to a world where sunsets tell a different story, where the familiar colors of evening are turned upside down in the most beautiful and unexpected way. Mars has blue sunsets. While we watch our sun sink into Earth's atmosphere wrapped in warm oranges and reds, on Mars the setting sun appears as a cool sapphire jewel against an alien sky, painting the horizon in shades of blue that would look more at home in our midday sky than our evening twilight. This isn't just a quirk of alien beauty, it's a story written in dust and light, a tale of how the tiniest particles can transform the grandest spectacles. Mars is a world perpetually painted in rust and amber, its entire surface covered in iron oxide, the same stuff that makes old metal rust red here on Earth. When windstorms sweep across the Martian landscape, they lift this fine, powdery dust high into the thin atmosphere, creating a permanent haze that gives the Martian sky its familiar butterscotch color during the day. But here's where the physics becomes poetry. Dust particles behave differently, with light depending on how that light encounters them. During the Martian day, when sunlight comes straight down through the atmosphere, these tiny rust-colored particles scatter light in a way that gives the sky its warm golden hue. But as the sun approaches the horizon during sunset, something magical happens. The sunlight must travel much farther through the dusty atmosphere, and during this longer journey, something extraordinary occurs. The dust particles, which spent all day scattering warm colors, begin to act differently. They start scattering blue light more effectively, the same blue light that gives Earth its azure skies during the day. It's as if Mars saves up all its blue light during the day and releases it in one beautiful burst as the sun sets. Picture standing on the rusty plains of Mars as the day ends. Around you stretches a landscape that looks like the American Southwest painted in sepia tones, all golden rocks and rust-colored sand dunes, extending to the horizon. The sky above has been a warm amber all day, like looking up through a piece of vintage glass. But now, as the sun touches the distant hills, something wonderful begins to happen. The sun itself starts to appear blue, not the fierce yellow-white we know from Earth, but a cool, gentle blue, like a sapphire held up to the light. The area around the sun begins to glow with the same impossible color, creating a pool of blue light spreading across the horizon. It's sunset in reverse, as if you're watching the sun rise on Earth, but with all the colors inverted, transformed, made alien and beautiful. This blue sunset isn't sharp and sudden. It's gentle and gradual, like watercolor paint slowly bleeding across paper. The blue glow spreads and softens, creating a moment of serene beauty that feels both utterly foreign and somehow familiar. It's the same sun that warms Earth, the same light that creates our golden sunsets, but filtered through a different world's atmosphere, transformed by different dust, scattered by different physics into something entirely new. And there's something profound about imagining this daily miracle happening on a world where no human eyes have yet witnessed it in person. Every Martian day for billions of years, the sun has been setting blue over empty plains and ancient river valleys, painting the sky in colors that would take our breath away, creating beauty with no audience, except perhaps the occasional robotic rover, faithfully recording these moments and sending them back to Earth for us to marvel at. The rovers that have landed on Mars have captured these blue sunsets in photographs that seem almost too beautiful to be real. When NASA first released images of Martian sunsets, people thought there must be some mistake, some error in the camera's color calibration. Surely sunsets couldn't be blue. But they are, and they're more beautiful for being so unexpected, so perfectly alien, yet somehow familiar. Think about what this means for any future human visitors to Mars. After a long day of exploring, of working, of building humanity's first foothold on another world, they'll have the privilege of watching the sun set blue over a landscape no earthbound human has ever seen. They'll witness beauty that exists nowhere else in our solar system, sunset colors that exist in no earthly sky. As you drift towards sleep tonight, carry with you this image of blue sunsets over rust-colored hills, a familiar light transformed by alien dust into something entirely new, and perhaps dream of standing on that distant world someday, watching our sun paint the Martian sky in impossible shades of blue, reminding you that even the most familiar things, light, dust, sunset, can create entirely new kinds of beauty when they dance together in different places, under different skies, in the endless creativity of our cosmic neighborhood. Fact 23. There's a hexagon on Saturn's north pole. Sometimes the universe reveals patterns so perfect, so geometrically precise, that they seem more like the work of a cosmic architect than the result of natural forces. Tonight, as you prepare for restful sleep, let me share with you one of the most mysteriously beautiful shapes in our solar system. A pattern so regular and persistent that when scientists first discovered it, they could hardly believe their instruments were telling the truth. There's a hexagon on Saturn's north pole. Earth once had two moons, according to the most romantic of planetary theories. The second, smaller companion that waltzed alongside our familiar moon for millions of years, before finally, inevitably, the two lunar partners collided in the slowest, gentlest cosmic embrace imaginable. Picture Earth as it was 4 billion years ago, when our planet was still finding its rhythm, still settling into the gravitational dance that would define its future. The continents were different shapes then, the atmosphere was a different color, and when night fell over this ancient world, two moons rose into the sky, our familiar beloved moon that still lights our nights today, and a smaller companion, perhaps 1/3 its size, trailing behind like a faithful celestial puppy, following its larger sibling across the star-filled darkness. This second moon, which scientists have whimsically named the Little Sister Moon, would have been beautiful in its own quiet way, not as bright as our current moon, not as dramatically present in the night sky, but visible enough to cast its own gentle shadows, to create its own tidal influences, to add a second rhythm to the cosmic music that was already beginning to shape life on our planet. Imagine the double shadows these two moons would have cast, the way they would have played hide-and-seek with each other as they orbited Earth, sometimes appearing close together like cosmic siblings, sometimes separated by vast stretches of star-filled sky. Ancient creatures, if they had eyes to see and minds to wonder, might have thought of them as companions, as partners in some celestial dance choreographed by forces beyond understanding. but this beautiful arrangement carried within it the seeds of its own ending. The two moons were locked in what astronomers call orbital resonance, a gravitational relationship where their orbits were mathematically connected, each moon's position influencing the other's path through space. Over millions of years, this delicate gravitational conversation gradually drew them closer together, like dancers slowly spiraling toward each other across a cosmic ballroom. The collision, when it finally came, wasn't the violent, explosive crash you might imagine from science fiction movies. Instead, it was probably the gentlest collision in the history of our solar system, a cosmic slow-motion embrace between two worlds that had been dancing together for eons. The smaller moon approached at just a few kilometers per hour, barely faster than a walking pace, and when they touched, it was more like a kiss than a collision. Rather than shattering into pieces, the little sister moon likely spread itself across the far side of our familiar moon like cosmic frosting, adding its mass to the lunar surface in a process so gradual that it took thousands of years to complete. This would explain one of the great mysteries about our moon, why the side we never see, the far side that's always turned away from Earth, has such a different composition and appearance from the side that faces us. The far side of the moon is covered in thicker crust, higher mountains, and different types of rock, as if it were built from different materials or formed through different processes. If the little sister moon theory is correct, then what we're seeing on the moon's far side is actually the remains of Earth's second moon, gently spread across the surface like a cosmic memory of what once was. This collision also explains why our moon is so unusually large compared to Earth. Most planets have moons that are tiny compared to their parent world, but our moon is about 1/4 the diameter of Earth, making the Earth-Moon system almost like a double planet. If our moon absorbed a second moon early in its history, that would account for its impressive size and its unusual composition. There's something deeply poetic about this theory, this idea that our current moon carries within it the remains of a companion we lost long ago. Every time you look up at the full moon, you might be seeing not just one celestial body, but two moons joined together. A cosmic love story written in rock and regolith across the surface of our nearest neighbor. As you drift towards sleep tonight, imagine those ancient double moonrises. Picture a time when Earth's sky held twice the lunar beauty it does today, and perhaps find comfort in knowing that even though we lost our second moon long ago, it didn't really disappear. It became part of the moon we still have, still lighting our nights, still pulling our tides, still inspiring poets and dreamers with its silver presence in our dark sky, carrying within itself the memory of a cosmic dance that ended in the gentlest of embraces. Fact 25. Space isn't silent, near Jupiter. We think of space as the ultimate silence, don't we? That perfect, profound quiet where no sound can travel, because there's no air to carry it. But tonight, as you prepare for peaceful sleep, let me share with you one of the universe's most beautiful secrets, that even in the vacuum of space there are songs being sung, melodies being composed, and Jupiter, that giant king of planets, is conducting one of the most haunting symphonies in our solar system. Space isn't silent near Jupiter. Radio waves emitted from its massive magnetic field can be picked up as eerie audio signals, creating a cosmic soundtrack that sounds like something from the dreams of whales mixed with the whispers of ancient spirits. Jupiter doesn't make sound in the way we understand it on Earth, where vibrations travel through air to reach our ears. Instead, it creates something far more subtle and strange, electromagnetic waves that dance through the vacuum of space at the speed of light, invisible rivers of energy that our radio telescopes can catch and translate into something our human ears can comprehend. These aren't random static or meaningless noise. Jupiter's radio songs have structure, rhythm, even something approaching melody. Scientists have recorded swooping whistles that rise and fall like celestial bird calls, rhythmic pulses that beat like a cosmic heart, and long, haunting tones that seem to carry the longing of deep space itself. When you listen to recordings of Jupiter's radio emissions, it's like eavesdropping on conversations between invisible giants, or hearing the universe humming to itself in frequencies we never knew existed. The source of this cosmic music is Jupiter's magnificent magnetic field, an invisible force field that extends millions of kilometers into space, trapping charged particles from the solar wind and accelerating them to incredible speeds. As these particles spiral around Jupiter's magnetic field lines, they create electromagnetic waves, And these waves, when translated into audio frequencies, become Jupiter's otherworldly voice. Picture Jupiter surrounded by vast, invisible rivers of energy, streams of charged particles flowing in complex patterns around the planet like cosmic aurora that extend far beyond what any eye could see. These particle streams interact with Jupiter's moons, particularly Io with its sulfur volcanoes, creating electromagnetic disturbances that add percussion to Jupiter's cosmic symphony, like drums made of magnetism and lightning. But Jupiter isn't singing alone. Its four largest moons, Io, Europa, Ganymede, and Callisto, each add their own voices to the celestial choir. Europa's icy surface creates electromagnetic whispers as Jupiter's magnetic field sweeps across Ganymede. The only moon in our solar system with its own magnetic field creates complex harmonies as its magnetic field interacts with Jupiter's. Even tiny Io contributes its volcanic voice, sending charged sulfur particles streaming into space to become part of Jupiter's magnetic orchestra. The most haunting of Jupiter's sounds are called chorus emissions, radio waves that when converted to audio sound remarkably like whale songs or the calls of exotic birds. These emissions rise and fall in pitch, creating melodies that seem almost intentional, almost composed, as if Jupiter were trying to communicate something profound across the emptiness of space. NASA's various missions to Jupiter have recorded hours of these cosmic songs, and listening to them is like discovering that the universe has been making music all along, just in frequencies we never thought to listen to. The Juno spacecraft currently orbiting Jupiter continues to record these electromagnetic symphonies, sending them back to Earth where scientists study them, not just for their scientific value, but for their strange alien beauty. There's something deeply moving about imagining Jupiter out there in the darkness, singing its electromagnetic songs to an audience of moons and cosmic dust, creating beauty that exists whether anyone is listening or not. For billions of years, these radio waves have been streaming out from Jupiter, carrying their haunting melodies into the void, waiting for someone to develop the technology to hear them. And it's not just Jupiter. Saturn has its own radio voice. Uranus creates its own electromagnetic whispers, and even our own Earth sings radio songs into space, though we're usually too busy making our own noise to notice our planet's contribution to the cosmic symphony. When you think about it, the universe suddenly seems less empty, less silent, more alive with invisible music and inaudible songs. Every magnetic field, every stream of charged particles, every interaction between electromagnetic forces creates its own unique voice in this cosmic choir that's been performing since the solar system began. As you close your eyes tonight, imagine Jupiter hanging in the darkness beyond our atmosphere, surrounded by its invisible magnetic symphony, its four large moons adding their voices to the cosmic chorus. And perhaps, in the quiet moments before sleep takes you, you might hear echoes of that distant music, those electromagnetic whale songs flowing through space, reminding you that even in the vast emptiness between worlds, the universe is never truly silent. It's just singing, in languages we're only beginning to learn how to hear. Fact 26. The sun sings. There's something magical about the idea of music in unexpected places, isn't there? Tonight, as you settle into the gentle rhythm of approaching sleep, let me tell you about the most ancient and constant song in our solar system, a melody that has been playing since before Earth existed, a cosmic symphony performed by our sun that creates music not with air and vibration, but with something far more fundamental and beautiful. The sun sings, not with sound as we know it, but with oscillations in its plasma that create musical notes we can interpret with sensitive instruments, a stellar song that has been playing for over 4 billion years. Imagine the sun not as a simple ball of fire, but as a vast musical instrument, larger than 1,000,000 Earths, where the instrument itself is made of plasma, so hot that atoms can't hold on to their electrons, where the music is created by pressure waves and magnetic fields, and the complex dance of nuclear fusion at the sun's core. This cosmic instrument creates frequencies and harmonies that, when translated into something our human ears can comprehend, sound like the deepest, most profound music you've ever heard. The sun's song comes from heliosysmology, the study of how the sun vibrates like a bell, deep inside the sun's core, where temperatures reach 15 million degrees Celsius. Nuclear fusion creates not just the light and heat that sustain all life on Earth, but also pressure waves that propagate outward through the sun's layers like ripples spreading across a pond. These waves bounce around inside the sun, reflecting off different density layers, creating standing wave patterns that make the entire surface of the sun pulse and vibrate in complex mathematical rhythms. Scientists have discovered that the sun oscillates in millions of different modes simultaneously, like a cosmic organ with millions of pipes, all playing at once. Some of these oscillations are so slow that they take hours to complete a single cycle, creating bass notes deeper than any earthly instrument could produce. Others oscillate faster, creating higher frequencies that, when compressed into human hearing range, sound like the ethereal tones of crystal singing bowls or the harmonic overtones of Tibetan meditation bells. The sun's surface rises and falls with these internal pressure waves, moving up and down by distances of just a few kilometers, tiny movements on the scale of the sun, but detectable by our most sensitive instruments. It's as if the sun is breathing, its entire surface expanding and contracting in patterns so complex and interwoven that they create a symphony of unimaginable richness and depth. But here's what makes this music even more remarkable. Each note, each frequency, each harmonic tells us something different about the sun's internal structure. Just as a doctor can listen to your heartbeat and learn about your health, astronomers can listen to the sun's music and understand what's happening in layers of the sun that we could never see directly. The deepest bass notes come from the sun's core, carrying information about nuclear fusion processes that occur in conditions more extreme than anything we can create on Earth. Higher frequencies originate from layers closer to the surface, telling us about temperature gradients and convection patterns that shape the sun's visible appearance. The sun's song isn't random or chaotic, it's incredibly organized, following mathematical patterns that reflect the fundamental physics of how stars work. Different regions of the sun sing in different keys, creating harmonies and resonances that reveal the sun's internal structure as clearly as an X-ray reveals the bones beneath our skin. It's as if the sun is constantly broadcasting its autobiography in the form of music, telling the story of its internal processes in frequencies and rhythms that span from seconds to hours. And this music isn't static, it changes over time, reflecting the sun's 11-year activity cycle. During solar maximum, when the sun's magnetic field is most active, and sunspots cover its surface, the music becomes more complex, more discordant, as magnetic fields interfere with the normal pressure wave patterns. During solar minimum, the sun's song becomes purer, more harmonious, as if the star is finding its natural voice again. Space missions have recorded the sun's music and made it available for anyone to hear. When you listen to these recordings compressed and translated into human hearing range, you hear something that sounds both alien and familiar, like whale songs mixed with wind chimes, like the deep resonance of a cathedral organ combined with the crystal-clear tones of tuning forks. It's music that seems to come from the very heart of creation itself. There's something profoundly moving about knowing that our sun, the source of all energy and life on Earth, is not just a nuclear furnace, but also a musical instrument of cosmic proportions. Every sunrise brings us not just light and warmth, but also the continuation of a song that began before our planet existed, and will continue long after we're gone. As you drift towards sleep tonight, imagine that ancient stellar music playing just beyond our atmosphere, the sun's deep bass notes and crystal harmonics flowing through space, a cosmic lullaby that has been singing Earth to sleep every night for billions of years, a reminder that even the most basic forces of nature, heat, light, nuclear fusion, can create beauty and music if we just learn how to listen. Fact 27. The Kuiper Belt, a second asteroid belt. Imagine standing in your backyard on a clear winter night, looking up at the stars and wondering what's out there beyond the planets we learned about in school. You know about Mars, Jupiter, Saturn, but what happens after Neptune? What exists in that vast, cold darkness at the edge of our solar system? Well, it turns out there's an entire neighborhood out there, a cosmic suburb if you will, that most people have never heard of. It's called the Kuiper Belt, and it's like discovering there's a second city beyond the one you thought was the last stop on the train line. Picture our solar system like a busy highway. We have the inner planets, Mercury, Venus, Earth, Mars, like the downtown area. Then there's the asteroid belt, that collection of rocky debris between Mars and Jupiter, like an old industrial district full of scattered building materials. Beyond that, we have the gas giants, Jupiter, Saturn, Uranus, Neptune, like grand suburban mansions with their own satellite communities. But here's where it gets interesting. After Neptune, about 30 times farther from the Sun than Earth, there's this second belt, not made of rock like the first one, but of ice. Lots and lots of ice. The Kuiper belt stretches out like a frozen wasteland, a place where the sun's warmth barely reaches, where temperatures hover around -200 degrees Celsius. This isn't just empty space with a few random chunks floating around. The Kuiper belt is populated with thousands, maybe millions of icy bodies. Some are tiny, no bigger than a city block. Others are massive, like Pluto, which was once considered our 9th planet before we realized it was actually just the most famous resident of this icy neighborhood. And then there's Eris, Pluto's slightly larger cousin, discovered in 2005, whose existence actually sparked the whole debate about what makes a planet a planet. These aren't just boring chunks of ice though, they're time capsules, frozen remnants from when our solar system was just forming, 4.5 billion years ago. Back then, everything was chaos. Dust and gas swirling around our young sun, gradually clumping together to form planets. The inner regions got hot enough to melt ice and rock, creating the terrestrial planets we know. But out in the Kuiper belt, it was so cold that water, methane and ammonia froze solid and stayed that way. Think of it like this. If our solar system were a house, the Kuiper belt would be like that old storage room in the basement where your family keeps everything from when you were little. Baby photos, old toys, things that tell the story of how everything began. These icy bodies carry the chemical signatures of our solar system's birth, preserved in the ultimate deep freeze. And here's something that might give you goosebumps on a quiet night like this. Some of these Kuiper belt objects occasionally get nudged by gravity, sent tumbling inward toward the sun. When they do, they heat up and develop those beautiful glowing tails we see in comets. That's right, many of the comets that have amazed humans throughout history, the ones that inspired myths and legends, actually began their journey in this distant, icy realm. The Kuiper belt reminds us that our solar system doesn't just end where we think it does. Beyond the familiar planets, beyond the comfortable boundary of Neptune's orbit, there's this vast, mysterious region full of ancient ice and forgotten worlds. It's a place where the sun looks like just another bright star, where the familiar rules of our inner solar system give way to something stranger and more wonderful. So the next time you're outside on a clear night, looking up at the stars, remember that, out there, far beyond what your eyes can see, there's an entire belt of ice worlds spinning slowly in the cosmic dark. They're the quiet guardians of our solar system's history, keeping the secrets of how everything began, waiting patiently in the cold for us to visit them and learn their stories. And maybe, just maybe, that thought will make the universe feel both more vast and more intimate at the same time. Act 28. Ceres has water vapor. Have you ever been so thirsty that you drink from a muddy puddle? Well, imagine being an astronomer, desperately searching the cosmos for signs of water, that precious substance that makes life possible, and discovering it in the most unexpected place, a dwarf planet, sitting right in our own backyard, in the asteroid belt between Mars and Jupiter. This is the story of Ceres, and it's a reminder that the universe loves to surprise us when we least expect it. For the longest time, we thought of the asteroid belt as a cosmic junkyard, a collection of rocky debris left over from when the planets formed, just chunks of stone and metal tumbling through space, interesting perhaps to mining companies in some distant future, but hardly the place you'd expect to find anything as life-giving as water. But Ceres was always a bit different. When Giuseppe Piazzi first spotted it through his telescope in 1801, he thought he'd found a new planet. Then astronomers realized there were many similar objects in that region, and they reclassified it as an asteroid. More recently, as we learned more about its size and composition, Ceres earned the title of dwarf planet, the same classification that Pluto received. Here's what makes Ceres special. It's not just the largest object in the asteroid belt, it's also round. That might not sound impressive, but in the world of space rocks, being round is actually a big deal. It means you have enough mass for your gravity to pull you into a sphere, rather than the potato shapes that most asteroids sport. Ceres is like the responsible older sibling in a family of unruly space rocks. But the real surprise came when the Dawn spacecraft arrived at Ceres in 2015. Scientists expected to find a dry, cratered world, maybe with some interesting geology, but nothing too exciting. Instead, they discovered something that made them rub their eyes and check their instruments twice. Water vapor. Not liquid water, mind you. It's far too cold for that. We're talking about something much more subtle. Imagine stepping outside on a cold winter morning and seeing your breath in the air. That's essentially what Ceres is doing. Except instead of exhaling warm air into cold atmosphere, It's sublimating, turning ice directly into vapor, without melting first. This discovery was like finding steam rising from what you thought was a completely dry desert. The water vapor appears to be coming from specific regions on Ceres, creating these ghostly plumes that drift up into space. It's as if this ancient world is quietly sighing, releasing whispers of water that have been locked away for billions of years. But here's where it gets even more intriguing. Scientists now believe that beneath Ceres's rocky surface, there might be an ocean, not a little puddle, but a real, honest-to-goodness ocean of liquid water, kept warm by radioactive decay in the dwarf planet's core, and insulated by a thick crust of rock and ice. Think about that for a moment. Right there in our asteroid belt, closer to us than Jupiter, there might be more liquid water than in all of Earth's oceans combined. It's like discovering that your quiet neighbor has been hiding an enormous swimming pool in their basement all these years. This possibility has scientists incredibly excited, because where there's liquid water, there's the potential for life. Not little green men, or space cities, but perhaps microscopic organisms, bacteria that could survive in the cold, dark environment beneath Ceres's surface. It would be life as we know it, chemically speaking, but living in conditions that would seem impossible to us surface dwellers. The story of Ceres reminds us that water, and possibly life, might be far more common in our solar system than we ever imagined. We've been looking toward Mars, Europa, and Enceladus as potential havens for life, but perhaps we should have been paying more attention to this modest dwarf planet that's been quietly harboring its secrets in the asteroid belt all along. So the next time you look up at the night sky, remember that somewhere out there, between the red dot of Mars and the bright light of Jupiter, there's a small world that's breathing water vapor into space, possibly hiding an ocean beneath its surface. It's a reminder that the universe is full of surprises, and sometimes the most extraordinary discoveries are hiding in the most ordinary places. Fact 29. Earth's magnetic field, once flipped. Have you ever held a compass and watched that little needle swing around, always finding north? There's something deeply comforting about magnetic north, this invisible, reliable constant that has guided sailors across oceans and hikers through forests for centuries. It feels as permanent as the sunrise, as dependable as gravity itself. But here's something that might make you look at that compass needle a little differently. There have been times in Earth's history when that needle would have pointed south instead of north. Times when our planet's entire magnetic field flipped upside down, like someone had picked up a giant bar magnet and turned it around. This isn't science fiction or some distant theoretical possibility. It's geology, written in stone, recorded in the very rocks beneath our feet. And it's happened hundreds of times throughout Earth's 4.5 billion year history. To understand how we know this, imagine you're an archaeologist, but instead of digging up pottery shards and ancient coins, you're studying layers of volcanic rock. When lava cools and hardens, tiny iron minerals inside it align themselves with Earth's magnetic field. Like microscopic compass needles frozen in time, they create a permanent record of which way magnetic north was pointing when that rock formed. Scientists have found these magnetic signatures in rocks all over the world, and what they reveal is extraordinary. The magnetic field doesn't just gradually drift or wobble, it completely reverses. North becomes south. South becomes north. As if the entire planet had suddenly decided to reorganize itself. The last time this happened was about 780,000 years ago, long before humans developed compasses or even understood what magnetism was. But if you had been there, standing on a hillside with some primitive magnetic needle, you would have watched it slowly swing around over the course of several thousand years, until it was pointing in completely the opposite direction. Now, you might be wondering what causes this cosmic game of magnetic musical chairs. The answer lies deep beneath our feet, in Earth's outer core, a churning ocean of liquid iron nearly 3,000 kilometers below the surface. This isn't the solid iron core at the very center, but a layer of molten metal that flows and swirls like a slow-motion hurricane. These flowing currents of liquid iron create electric currents, and electric currents create magnetic fields. It's the same principle that makes an electromagnet work, except we're talking about an electromagnet the size of a planet, powered by the heat left over from Earth's formation billions of years ago. But this system isn't perfectly stable. Sometimes the flow patterns change. The currents that normally reinforce our north-south magnetic field weaken or get disrupted. Imagine a river that normally flows steadily in one direction suddenly developing swirls and eddies that start flowing backward. Eventually, those backward currents can become strong enough to overwhelm the original flow, During a magnetic reversal, our protective magnetic field doesn't just flip, it weakens dramatically first. For several thousand years, Earth's magnetic shield becomes patchy and unreliable, like an umbrella full of holes. This is potentially problematic because our magnetic field is what protects us from harmful solar radiation and cosmic rays. Without that protection, more radiation reaches Earth's surface. The atmosphere itself provides some shielding, but not as much as we're used to. Some scientists think these periods of weakened magnetic protection might have influenced evolution, possibly contributing to extinction events or spurring evolutionary changes as species adapted to higher radiation levels. And here's something that might make you pause during your next compass reading. We're overdue for another reversal. The average time between flips is roughly 450,000 years, and it's been 780,000 years since the last one. Moreover, scientists have noticed that Earth's magnetic field has been weakening over the past few centuries. Does this mean we're about to experience a magnetic reversal in our lifetime? Probably not. These processes unfold over thousands of years, not decades. But it's a reminder that even the most fundamental aspects of our planet, things we take for granted like magnetic north, are actually dynamic, ever-changing features of a living world. So the next time you use a compass, take a moment to appreciate not just where that needle is pointing, but the incredible planetary machinery that makes it point there. And remember that someday, thousands of years in the future, that same needle might point in exactly the opposite direction, guided by the same powerful forces that have been shaping our world since long before the first human ever wondered which way was north. Fact 30. Mercury's double sunrise. Picture this. You're standing on the surface of Mercury, the closest planet to our sun, watching what you think will be a normal sunrise. The sun appears on the horizon, a brilliant disk much larger than it looks from Earth. You shield your eyes and watch it climb slowly into the star-filled sky. Remember, Mercury has no atmosphere, so you can see stars even during the day. But then something strange happens. The sun stops climbing. It hovers for a moment, then begins to sink back toward the horizon. Just when you think it's about to set again, it stops once more, reverses direction, and rises again, this time for good. You've just witnessed one of the most peculiar phenomena in our solar system, Mercury's double sunrise. This isn't magic or some optical illusion. It's the result of Mercury being caught in a cosmic dance between two competing rhythms. Its orbit around the sun and its rotation on its axis, and the sun's gravity winning the tug-of-war in the most unexpected way. To understand how this happens, we need to talk about Mercury's unusual relationship with time. You see, Mercury is tidally locked with the sun, but not in the way you might expect. It's not like our moon, which always shows the same face to Earth. Instead, Mercury has what scientists call a 3-to-2 resonance. For every 3 times Mercury spins on its axis, it completes exactly 2 orbits around the sun. This creates a situation where a single day on Mercury, one sunrise to the next, last 176 Earth days. That's longer than Mercury's year, which is only 88 Earth days. Think about that. On Mercury, days are longer than years. It's like having a job where your lunch break lasts longer than your entire workday. But here's where the double sunrise comes in. Because Mercury follows such an elliptical orbit, its distance from the sun changes dramatically as it travels around. When Mercury is closest to the sun, at a point called perihelion, the sun's gravitational pull causes the planet to speed up in its orbit, just like a skater spinning faster when they pull their arms in. During these periods, Mercury's orbital speed temporarily becomes faster than its rotation speed. From the perspective of someone standing on Mercury's surface, this makes the sun appear to slow down, stop, and even move backward briefly across the sky before resuming its normal eastward journey. It's as if you were on a merry-go-round that was spinning at a steady pace. But the entire merry-go-round was also traveling around a track, and sometimes the track motion got faster than the spinning motion. From your perspective on the merry-go-round, the scenery would seem to slow down, stop, and even go backward occasionally. This phenomenon only happens in certain regions of Mercury. If you were standing at one of the hot poles, the 2 points on Mercury's equator that face the sun directly when the planet is at perihelion, you'd experience the most dramatic double sunrise. The sun would appear enormous in the sky, about 10 times larger than it looks from Earth, and would perform this celestial dance of stopping and starting. The temperature during these double sunrises reaches over 400 degrees Celsius, hot enough to melt lead. The surface becomes a hellish landscape of extremes, where rocks glow like coals, and any water would instantly boil away into space. But perhaps the most mind-bending aspect of Mercury's double sunrise is what it tells us about the nature of time itself. We're used to thinking of sunrise and sunset as the most regular, predictable events in our lives. They're how humans have measured time for millennia. Yet, on Mercury, even the sun's movement across the sky becomes complex and unpredictable. It's a reminder that our earthbound experience of time, with its neat 24-hour days and predictable sunrises, is just one possible way for a world to experience the passage of time. Throughout the universe, there are planets where days last longer than years, where the sun rises twice, where the familiar rhythms we depend on would seem completely alien. On quiet mornings, when you watch the sun rise steadily and predictably in the east, remember that somewhere else in our solar system, on a small crater-covered world racing around the sun, another sunrise is happening, one that stops, reverses, and starts again, painting the sky with possibilities we can barely imagine. It's a beautiful reminder that even something as simple as sunrise can become poetry, when seen from a different perspective, in a different world, under different skies. Fact 31. Triton orbits Neptune, backwards. Imagine you're at a crowded train station, watching the flow of people moving through the terminal. Everyone is walking in roughly the same direction, following the natural patterns of movement, heading toward their platforms in an orderly fashion. Then suddenly, you notice one person walking confidently in the opposite direction, pushing against the crowd, moving with purpose but completely counter to everyone else. That person is Triton, and the train station is the Neptune system. In our solar system, almost everything follows the same basic rule of rotation. The planets orbit the sun in the same direction. Most moons orbit their planets in that same direction. It's like a vast cosmic clockwork, all the gears turning in harmony, all moving in the same rotational sense that the original solar nebula was spinning 4.5 billion years ago. But Triton is different. This large, icy moon of Neptune moves in what astronomers call a retrograde orbit. It circles Neptune in the opposite direction from almost every other major moon in the solar system. It's not just slightly off, like a dancer who's a half step behind the music. It's moving in completely the wrong direction, as if it's decided to waltz while everyone else is doing the foxtrot. This backward dance tells us that Triton has a story, and it's not the story of a typical moon. Most moons form from the same disk of material that created their parent planet. They condense from leftover debris, gradually accumulating into spherical bodies that naturally orbit in the same direction as their planet's rotation. It's a tidy, predictable process that creates stable, well-behaved moons. But Triton is almost certainly not a native of the Neptune system. It's an immigrant, a refugee from somewhere else entirely. Scientists believe Triton was once a Kuiper Belt object, one of those icy worlds that live in the frozen outer reaches of our solar system, beyond the orbit of Neptune. Perhaps it was similar to Pluto, or maybe it had a companion, dancing in a binary pair through the cold darkness at the edge of our solar system. Then about 4 billion years ago, something dramatic happened. During the early, chaotic period of our solar system's history, when planets were still migrating and gravitational interactions were reshaping orbits, Triton wandered too close to Neptune. Or perhaps Neptune, still settling into its final orbit, encountered Triton during its own migration. What followed was a gravitational mugging. Neptune's immense gravity reached out and captured Triton, pulling it away from its original orbit, and trapping it in the Neptune system. But when you capture something moving in a different direction, it keeps that original motion. Triton didn't gently settle into a nice orderly orbit. It was yanked into a backward path around its new home. This capture wasn't gentle. It would have been a violent, chaotic process that likely disrupted Neptune's entire moon system. Any original moons that Neptune might have had were probably destroyed or flung away into space. Triton became Neptune's new primary moon, but at a terrible cost to the system's original inhabitants. And here's where the story takes both beautiful and tragic. Triton is slowly spiraling inward toward Neptune. Because it's orbiting backward against Neptune's rotation, tidal forces are gradually stealing energy from its orbit. Every year, Triton moves about 3.5 centimeters closer to Neptune. It's an incredibly slow process, but it's inexorable. In about 3.5 billion years, Triton will reach what's called the Roche limit, the point where Neptune's gravity will overcome Triton's own gravitational hold on itself. When that happens, this large, fascinating moon will be torn apart, shredded into a ring of debris around Neptune. It will become a spectacular ring system, possibly more dramatic than Saturn's rings, but it will mean the end of Triton as a world. Think about that timeline for a moment. Our sun will still be shining, Earth might still exist, but Neptune will have gained magnificent rings at the cost of its largest moon. It's cosmic recycling on an unimaginable scale. Triton's backward orbit also affects its surface in unique ways. The moon experiences extreme seasonal changes as it moves around Neptune, with seasons lasting about 40 years each. During Triton's summer, nitrogen ice sublimates from its surface, creating a thin atmosphere, and even nitrogen geysers that shoot material several kilometers into space. So the next time you look up at the night sky and think about the orderly dance of celestial bodies, remember Triton, the rebel moon that moves to its own rhythm, the captured wanderer slowly spiraling toward its ultimate transformation. It's a reminder that even in the vast, apparently stable cosmos, there are stories of disruption, capture, and inevitable change, playing out over timescales that dwarf human comprehension, but follow the same gravitational laws that keep our feet planted on Earth. Fact 32. Mars has 2 tiny potato-shaped moons. When you look up at our moon on a clear night, it's easy to take for granted just how perfect it is. Round, bright, large enough to create beautiful eclipses, small enough to fit comfortably in our sky. It rises majestically over the horizon, goes through its elegant phases, and has inspired countless poems, songs, and love stories throughout human history. But imagine if instead of our one magnificent moon, Earth had 2 tiny lumpy rocks, tumbling chaotically overhead. That's the reality for Mars, whose 2 small moons, Phobos and Deimos, are about as different from our moon as you could possibly imagine. These aren't the kind of moons that inspire romantic poetry. Phobos, the larger of the 2, is only about 27 kilometers across at its widest point. You could drive across it in about 20 minutes on a highway. Deimos is even smaller, roughly 15 kilometers across. If you parked them next to each other, in the parking lot of a major city, they'd take up less space than the downtown area. But it's not just their size that makes them unusual. Both moons are shaped like potatoes, irregular, lumpy, crater-scarred potatoes that look like they've been through a cosmic food fight. They don't have enough mass for gravity to pull them into spheres, so they maintain these odd, angular shapes that make them look more like asteroids than moons. And that's probably exactly what they are. The story of how Mars acquired these 2 tiny companions is likely a tale of gravitational piracy. Early in the solar system's history, when things were much more chaotic than they are today, Mars probably reached out with its gravity and captured 2 passing asteroids. Perhaps they were wandering alone through the space between Mars and Jupiter. Or maybe they were part of a larger group that got broken up by gravitational interactions. Mars said, in effect, "You 2 look lonely. Why don't you stay?" And they've been circling the red planet ever since, like 2 faithful, but very odd pets. Their names come from Greek mythology. Phobos means fear, and Deimos means dread. They were the sons of Ares, the god of war, and appropriate companions for Mars, the Roman god of war. But despite their intimidating names, these little moons are more endearing than frightening. Phobos, the inner moon, races around Mars in just 7.5 hours, faster than Mars rotates. This means that if you were standing on Mars watching Phobos rise in the west, you'd see it cross the entire sky and set in the east in just over 4 hours. Then, about 11 hours later, it would rise again. Some Martian days you might see Phobos rise and set twice. Deimos, the outer moon, takes about 30 hours to orbit Mars, so it moves more slowly across the Martian sky. From Mars's surface, it would look like a bright star rather than what we'd recognize as a moon. Both moons are so small and reflect so little light that even when they pass in front of the sun, they don't create total solar eclipses, just tiny shadows that drift across the Martian landscape. Here's something that might give you pause. Phobos is doomed. Because it orbits so quickly and so close to Mars, tidal forces are gradually pulling it closer to the planet. Every year, Phobos drops about 2 centimeters closer to Mars. In about 50 million years, it will either crash into the Martian surface or be torn apart by tidal forces, possibly creating a thin ring around Mars. When that happens, Mars will briefly become a ringed planet, joining the ranks of Jupiter, Saturn, Uranus, and Neptune. But unlike the magnificent ice and rock rings of the gas giants, Mars's ring will be made of the broken pieces of poor little Phobos, a celestial funeral pyre for a moon that spent eons faithfully circling its adopted home. Scientists have proposed that we could visit these moons before Phobos meets its fate. They're so small that landing on them would be more like docking with a space station than landing on a world. The gravity is so weak that you could probably jump clean off the surface if you tried. There's something both humbling and poetic about Mars's two little moons. They remind us that not every world gets a perfect round moon like ours. Some planets have dozens of moons, some have none. And some, like Mars, have two small, irregular companions that were probably just passing through the neighborhood billions of years ago and decided to stay. They're a reminder that the solar system is full of these smaller stories, not just the grand narratives of massive planets and spectacular phenomena, but also the quiet tales of little potato-shaped rocks that faithfully orbit their adopted home, year after year, even as one of them slowly spirals toward its inevitable end. The next time you see Mars as a red dot in the night sky, remember that it has company up there, two tiny, lumpy moons keeping it company in the cosmic dark. Fact 33. A year on Neptune lasts 65 Earth years. Imagine being born, living your entire life, growing old, and dying, all while a distant world completes less than half of a single trip around the Sun. That's the reality of Neptune, the eighth and outermost planet in our solar system, where a single year stretches across 165 Earth years. To put this in perspective, Neptune was discovered in 1846 by German astronomer Johann Galle, based on mathematical predictions by Urbain Le Verrier and John Couch Adams. They noticed that Uranus wasn't following its predicted orbit perfectly. Something was tugging at it gravitationally. That something turned out to be Neptune, hiding in the cold darkness beyond Uranus. Here's the remarkable thing. Neptune didn't complete its first full orbit since its discovery until July of 2011. Think about that. When Neptune was first spotted through telescopes, slavery was still legal in the United States. The American Civil War hadn't happened yet, and the light bulb wouldn't be invented for another 33 years. Napoleon had died just 25 years earlier. Charles Darwin was still 7 years away from publishing On the Origin of Species. Every person who first observed Neptune, the astronomers who calculated its position, the scientists who confirmed its existence, everyone who marveled at this new addition to our solar system, lived their entire lives and died while Neptune was still completing that first observed orbit. This incredible orbital period exists because Neptune is almost 30 times farther from the Sun than Earth is. At that distance, the Sun appears as just a bright star in Neptune's sky, providing roughly 1,000th of the warmth and light that we receive here on Earth. It's a cold, dark world where high noon looks more like twilight on Earth. But distance alone doesn't tell the whole story. Neptune's orbital mechanics follow Kepler's laws, which tell us that the farther a planet is from the Sun, the slower it moves in its orbit. Neptune plods along at about 5.5 kilometers per second, compared to Earth's zippy 30 kilometers per second. It's like the difference between a leisurely stroll and a sprint. During Neptune's long year, entire civilizations could rise and fall on Earth. The Roman Empire lasted about 500 years. That's only 3 Neptune years. The entire history of the United States, from the Declaration of Independence to today, spans less than 1.5 Neptune years. Human beings have been practicing agriculture for only about 60 Neptune years. But here's something that adds even more perspective to Neptune's leisurely orbital pace. We've been aware of this planet for such a tiny fraction of its year that we're still learning basic things about it. The Voyager 2 spacecraft, which flew by Neptune in 1989, gave us our only close-up look at this distant world. That flyby happened just over half a Neptune year ago, which means we've observed Neptune up close for only about 0.2% of its orbital period. Imagine trying to understand a person's entire life story based on watching them for about 43 minutes. That's roughly equivalent to how much of Neptune's year life we've been able to observe closely. What we have learned is fascinating. Despite being so far from the Sun, Neptune is surprisingly active. It has the fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour. These winds blow in the opposite direction of the planet's rotation, and no one is entirely sure what drives them. It's like discovering that the most remote, seemingly sleepy town in the world actually has the most intense nightlife. Neptune also has a dynamic atmosphere with changing weather patterns. Large storm systems, some the size of Jupiter's Great Red Spot, appear and disappear over periods of several years, since a few years to death is just a tiny fraction of Neptune's year. We're essentially watching rapid weather changes during what amounts to a few moments of Neptune's annual cycle. The planet has 14 known moons, including Triton, which orbits backward and is probably a captured Kuiper Belt object. It also has a faint ring system, discovered only when Voyager 2 flew by. These rings are named after astronomers involved in Neptune's discovery: Gallia, Leverrier, and Adams, a fitting tribute to the people who found this distant world through pure mathematical detective work. As we sit here on Earth, completing our annual journey around the Sun in a comfortable 365 days, it's worth remembering that Neptune is still out there, slowly making its way through that same journey we complete so quickly. When Neptune finishes its next complete orbit, it will be the year 2176. The children born today will be old when that happens, and their great-great-grandchildren will be the ones to witness Neptune's third observed complete journey around our Sun. There's something both humbling and wondrous about this cosmic perspective on time, the reminder that while we measure our lives in years, the universe operates on scales that dwarf human experience, where a single planetary year can encompass the entire span of recorded human history. Fact 34. The Sun will eventually engulf Earth. There's something deeply comforting about the Sun. It rises every morning, sets every evening, and has been doing exactly that for as long as humans have existed. It seems eternal, unchanging, as dependable as anything in our universe. We plan our days around it, our seasons depend on it, and all life on Earth exists because of its steady, reliable warmth. But like everything else in the universe, our Sun has a story with a beginning, a middle, and an end. And that ending, while unimaginably far in the future, involves our Earth in a way that's both spectacular and terminal. The Sun is currently what astronomers call a main sequence star, middle-aged, stable, burning hydrogen in its core, and converting it to helium through nuclear fusion. It's been doing this for about 4.5 billion years, and it's got roughly another 5 billion years of this steady burning ahead of it. To put that in perspective, 5 billion years ago, Earth was still forming, and life on our planet consisted of nothing more complex than single-celled organisms. But eventually the Sun will start running out of hydrogen fuel in its core. When that happens, the delicate balance that has kept our star stable for billions of years will begin to shift. The core will start contracting under its own gravity, getting hotter and denser. This will cause the outer layers of the Sun to expand dramatically. Our Sun will become what's called a red giant star. Imagine a balloon being inflated, but instead of air, it's being filled with the outer layers of a star. The Sun's surface will expand outward, growing larger and larger, reaching first to Mercury's orbit, then to Venus's orbit, and finally, to Earth's orbit and beyond. During this red giant phase, which will last for about 1 billion years, the Sun will be hundreds of times larger than it is today. From Earth's perspective, if Earth still exists and if anyone is somehow still around to see it, the Sun will fill a significant portion of the sky. It will be a dim red, enormous disk that stretches across the heavens like a cosmic umbrella. The Sun's surface temperature will actually be cooler than it is today, which is why it will appear red rather than the yellow-white we're used to. But because it will be so much larger, it will still be putting out much more total energy. Earth will be baked by temperatures hot enough to vaporize rock. Long before the Sun physically reaches Earth's orbit, our planet will already be uninhabitable. The increased solar radiation will boil away Earth's oceans, strip away its atmosphere, and turn the surface into a hellish wasteland. Any life that somehow survived the early stages of the Sun's expansion will be long gone by the time the Sun's outer layers actually reach us. When the Sun's expanding atmosphere finally does engulf Earth, our planet will experience what's called atmospheric drag. Earth will essentially be orbiting inside the Sun's extended thin atmosphere. This will cause Earth to spiral inward, like a satellite slowly losing altitude and falling back to Earth. Except in this case, Earth will be falling into the Sun. The final act will be relatively quick on cosmic timescales. Earth will spiral through the Sun's outer layers, heating up from friction until it simply vaporizes, becoming part of the Sun itself. Our entire planet, every mountain, ocean building and grain of sand, will be dissolved into the solar atmosphere. But this isn't really the end of the story. After the Sun has expanded to its maximum size as a red giant, it will begin to shed its outer layers, creating beautiful planetary nebulae, those colorful, glowing clouds of gas that we see scattered throughout our galaxy. What remains will be a white dwarf star, about the size of Earth but incredibly dense, slowly cooling over trillions of years. The atoms that once made up our planet will be scattered into space, eventually becoming part of new stars, new planets, new worlds. In a sense, Earth won't be destroyed. It will be transformed, recycled, given a new existence as part of the ongoing cosmic story. There's something both sobering and oddly comforting about this ultimate fate. It reminds us that even the most permanent-seeming things in our universe are temporary. The sun that seems so eternal, the earth that feels so solid beneath our feet, even the mountains that appear to be permanent fixtures, all of it is part of a much larger story of cosmic evolution. But 5 billion years is a length of time that's almost impossible to comprehend. If all of human history were compressed into a single day, 5 billion years would be equivalent to more than 3 million years. Entire species will evolve and go extinct millions of times over before the sun begins its red giant phase. Our descendants, if they still exist, will be as different from us as we are from bacteria. And who knows, by then, humanity or whatever we become might have long since left Earth behind, spreading to other star systems, other worlds. We might look back at Earth from distant planets orbiting younger stars, watching our old home's final dance with the sun as a piece of ancient history. The way we now look back at the formation of the moon or the end of the dinosaurs, the sun's eventual engulfment of Earth is a reminder that everything in the universe operates on multiple timescales simultaneously. While we go about our daily lives thinking in terms of years and decades, the cosmos is playing out dramas that span billions of years. It's humbling and awe-inspiring at the same time, a reminder that we're part of something much larger and more amazing than our everyday experience might suggest. Fact 35. Earth's core is hotter than the sun's surface. Deep beneath your feet, farther down than you could ever dig, past the basement, past the bedrock, past miles and miles of solid rock. There's something that might surprise you. It's hotter down there than the surface of the sun. This seems impossible, doesn't it? The sun is this brilliant ball of nuclear fire hanging in space, so bright you can't look directly at it, so hot it can give you a sunburn from 93 million miles away. Meanwhile, Earth's core is just rock and metal, sitting quietly beneath us, never bothering anyone, never blazing across the sky. How could the inside of our seemingly peaceful planet be hotter than the surface of our star? The answer lies in understanding two very different kinds of heat, generated in two very different ways. Let's start with the sun's surface, which scientists call the photosphere. It's the layer we see when we look at the sun, the bright yellow-white disk that lights up our days. The temperature there is about 5,500 degrees Celsius, hot enough to vaporize any material we know of, hot enough to turn a car into plasma in milliseconds. But now let's journey to the center of our Earth. We'd travel through the crust, that thin skin of rock we live on, then through the mantle, a thick layer of hot, slowly flowing rock, then through the outer core, a churning ocean of liquid iron and nickel, and finally, we'd reach the inner core, a ball of solid iron and nickel, about the size of the moon, where temperatures reach over 6,000 degrees Celsius. That's right, Earth's core is actually hotter than the surface of the sun. This seems to violate our intuitive understanding of how things work. Shouldn't the sun, with all its nuclear fusion and blazing energy, be hotter than a planet? But remember, we're comparing the sun's surface to Earth's core. If we compared Earth's core to the sun's core, where nuclear fusion actually happens, the sun would win easily. Temperatures there reach 15 million degrees Celsius. But how does Earth's core get so incredibly hot? It's not from nuclear fusion like the sun. Instead, Earth's internal heat comes from three main sources, like three different furnaces all running at once. First, there's leftover heat from when Earth formed 4.5 billion years ago. Picture the early solar system as a cosmic construction site, with chunks of rock and metal constantly smashing together. Every collision converted motion into heat. As Earth grew larger and larger from these impacts, all that collision energy got trapped inside, and our planet is still slowly cooling down from that primordial heat. Second, there's heat from radioactive decay. Deep inside Earth are radioactive elements, like uranium, thorium, and potassium, that have been slowly decaying since the planet formed. As these atoms break apart, they release energy in the form of heat. It's like having billions of tiny radioactive furnaces scattered throughout the planet, each one contributing a small amount of warmth that adds up to enormous amounts of energy over geological time. Third, there's heat, generated by the immense pressure itself. Imagine trying to squeeze a tennis ball in your hands. It would warm up slightly from the compression. Now imagine that pressure multiplied by millions. At the center of Earth, the pressure is about 3.5 million times greater than atmospheric pressure at sea level. This compression generates heat all by itself. All of this heat has nowhere to go quickly. Earth is an excellent insulator. Rock doesn't conduct heat very well, so the energy generated in the core takes millions of years to work its way to the surface. It's like wrapping the core in the world's thickest, most effective blanket. This trapped heat drives some of the most important processes on our planet. It powers the convection currents in the outer core that generate Earth's magnetic field, the same magnetic field that protects us from harmful solar radiation. It drives the movement of tectonic plates, causing earthquakes, volcanic eruptions, and mountain building. It's the engine that keeps our planet geologically active. Without this internal heat, Earth would be a cold, dead world. There would be no volcanism to recycle carbon and regulate our climate. No tectonic activity to create new land and refresh the surface. No magnetic field to shield us from space radiation. Earth would be more like Mars, a frozen, geologically inactive planet with a thin atmosphere and no protection from cosmic rays. So the next time you feel the solid ground beneath your feet, remember that you're standing on the thin, cool crust of a planet that's hotter at its center than the surface of the sun. We live on the skin of a world that's essentially a giant, slow-burning furnace, one that's been keeping our planet warm and active for billions of years and will continue to do so for billions more. It's a reminder that even the most familiar things, like the ground we walk on, can hold incredible secrets when we look deeper, literally deeper in this case, to the blazing heart of our world. Fact 36. Enceladus has icy geysers. Sometimes the most extraordinary discoveries come from the places we least expect them. Saturn has 62 known moons, and for a long time, most of them seemed like unremarkable chunks of ice and rock, quietly orbiting the ringed planet in the cold darkness of the outer solar system. Enceladus, the sixth largest of Saturn's moons, was just another small, icy world in this cosmic collection, until we looked closer and discovered something that changed everything. Enceladus is tiny, only about 500 kilometers across, small enough that you could drive around its equator in about 5 hours on Earth highways. It's covered in a brilliant white coating of fresh ice that makes it one of the most reflective objects in the solar system. For years, scientists assumed it was just another frozen, geologically dead moon, locked in perpetual winter at Saturn's distance from the Sun. But in 2005, NASA's Cassini spacecraft flew close to Enceladus and spotted something that made scientists around the world sit up and take notice: enormous geysers of water and ice crystals erupting from the moon's south pole, shooting hundreds of kilometers into space. Picture this. You're looking at what you think is a completely frozen, lifeless world, and suddenly you see massive plumes of water vapor and ice particles founting up from its surface like cosmic geysers, backlit by Saturn's pale light. It's like discovering that an apparently dormant volcano is actually very much alive, except instead of lava, it's shooting water into space. These aren't small, gentle emissions. The geysers on Enceladus erupt with tremendous force, launching material at speeds of up to 400 meters per second, fast enough that some of it escapes the moon's weak gravity entirely and becomes part of Saturn's ring system. In fact, scientists now believe that Enceladus is the primary source of material for Saturn's faint E-ring. The geysers emerge from what are called tiger stripes, 4 parallel fractures in the ice near Enceladus's south pole, each about 130 kilometers long and roughly 2 kilometers wide. These aren't random cracks, they are active geological features, warmer than the surrounding terrain, suggesting that something is generating heat beneath the surface. But here's what makes this discovery truly exciting. Where there are geysers of liquid water, there might be an ocean. And where there's an ocean, there's the possibility of life. Scientists now believe that beneath Enceladus's icy crust lies a global ocean of liquid water, kept warm by tidal heating. As Enceladus orbits Saturn, The planet's gravity stretches and squeezes the moon slightly, and this constant flexing generates heat through friction, just like how a paperclip gets warm if you bend it back and forth repeatedly. This hidden ocean is likely 10 kilometers deep, deeper than any ocean on Earth, and contains more water than Lake Superior. It's a vast, dark sea trapped beneath kilometers of ice, warmed from below by tidal forces, and possibly by hydrothermal vents on the ocean floor, similar to the ones we find in Earth's deepest oceans. The Cassini spacecraft actually flew through these geysers multiple times, analyzing their composition like a cosmic atmospheric scientist sampling volcanic emissions. What it found was remarkable. Not just water vapor and ice, but also organic compounds, carbon-based molecules that are the building blocks of life as we know it. The geysers also contain salt, suggesting that the water is in contact with rocky material at the bottom of the ocean, possibly creating the kind of chemical environment where life might arise. On Earth, some of our most ancient and resilient life forms thrive in similar conditions. In the dark, high-pressure environments around deep-sea hydrothermal vents, where they derive energy not from sunlight but from chemical processes. Could there be life in Enceladus's hidden ocean? Microscopic organisms, adapted to the cold and dark, living around hydrothermal vents, on the ocean floor, completely independent of the sun's energy. It's possible. The basic ingredients are there: liquid water, organic compounds, and an energy source. The geysers of Enceladus represent something profound. They're a direct connection between this hidden ocean and the space around Saturn. Every time they erupt, they're bringing samples from that dark subsurface sea up into space where we can study them. It's as if this distant moon is providing us with a natural sampling system, offering us glimpses of what lies beneath its icy shell. Future missions might be able to analyze these geyser emissions in even greater detail, or even send probes to land near the Tiger types and study the chemistry of the ejected material. Some scientists have even proposed sending a probe that could dive through the ice and explore the ocean directly, though such a mission would be incredibly challenging with current technology. For now, the geysers of Enceladus continue to fountain into space, carrying with them the secrets of one of the most potentially habitable environments in our solar system. They remind us that even in the cold, distant reaches of the outer solar system, there are worlds of liquid water, possibly harboring the conditions for life. Facts 37. Uranus and Neptune may have diamond rain deep in the atmospheres of our solar system's ice giants. Something extraordinary might be happening. Something that would make every jewelry store on Earth seem quaint by comparison. Scientists believe that Uranus and Neptune, those distant blue-green worlds at the edge of our solar system, might experience weather unlike anything we see on Earth. Storms that rain diamonds. This isn't science fiction or wishful thinking. It's a serious scientific hypothesis based on our understanding of extreme pressure, temperature, and chemistry in environments more alien than anything we can easily imagine. To understand how this might work, we need to journey into the hearts of these distant worlds. Both Uranus and Neptune are classified as ice giants, but don't let the name fool you. They're not made of the kind of ice you'd find in your freezer. They're composed largely of water, methane, and ammonia ices, mixed with rock and metal, all compressed under crushing gravitational pressure. As you descend through the atmosphere of these planets, the pressure and temperature increase dramatically. In the upper atmosphere, temperatures hover around -200 degrees Celsius, but deeper down, as the weight of thousands of kilometers of atmosphere presses down, temperatures rise to thousands of degrees. The key ingredient in this cosmic alchemy is methane. Both Uranus and Neptune have significant amounts of methane in their atmospheres. It's actually what gives them their beautiful blue-green color, as methane absorbs red light and reflects blue. But under the extreme conditions deep in these planets' interiors, methane molecules can be broken apart by pressure and heat. When methane molecules are subjected to pressures millions of times greater than Earth atmospheric pressure and temperatures of several thousand degrees, the carbon atoms can separate from the hydrogen atoms, and here's where the magic happens. Under these conditions, carbon atoms can bond together in the crystalline structure we know as diamond. Scientists have actually recreated some of these conditions in laboratories here on Earth, using diamond anvil cells and laser heating to simulate the extreme environments inside ice giants. In these experiments, they've successfully converted methane into diamond under pressures and temperatures similar to what we'd expect to find inside Uranus and Neptune. But the process might be even more dramatic than simple chemical conversion. Computer models suggest that these diamonds might actually condense out of the hot, compressed atmosphere like raindrops forming in a storm cloud. Picture it. In the deep atmospheres of these distant worlds, Tiny diamond crystals might form and then fall like glittering rain through layers of superheated gas. These wouldn't be small diamonds either. The models suggest that the diamonds could grow to significant sizes as they fall, perhaps as large as hailstones, or even bigger. Imagine diamond chunks the size of golf balls, or even larger, tumbling through the crushing depths of an alien atmosphere. As these diamond hailstones fall deeper into the planet, they encounter even more extreme conditions. Eventually they might reach depths where the pressure is so intense that even diamond begins to melt, creating liquid diamond oceans. It's a concept that pushes the boundaries of our imagination, vast seas of liquid carbon, existing under pressures that would instantly crush any spacecraft we could build. The implications of diamond rain go beyond just being an interesting curiosity. If this process is really happening, it could help explain some puzzling observations about these planets. Both Uranus and Neptune generate more heat internally than they should, based solely on leftover heat from their formation. The energy released by methane converting to diamond and then diamond melting under pressure could be one source of this excess heat. This process might also help explain the unusual magnetic fields of both planets. Unlike Earth's magnetic field, which is generated by our liquid iron core, the magnetic fields of Uranus and Neptune are tilted and offset from their rotational axes. If there are layers of electrically conductive liquid diamond deep in their interiors, this could affect how magnetic fields are generated. There's also the tantalizing possibility that similar processes might occur on other worlds. Some scientists speculate that diamond rain might fall on gas giants around other stars, or even on large moons in our own solar system under the right conditions. Of course, these diamond riches are forever beyond our reach. Even if we could somehow travel to Uranus or Neptune, we couldn't simply scoop up the diamonds. They exist under pressures that would destroy any conceivable mining equipment, and at temperatures that would vaporize most materials instantly. But there's something beautiful about the very idea that in the cold, distant reaches of our solar system, far from the warmth of the sun, nature might be creating the most precious gems in conditions of unimaginable extremity. It's a reminder that the universe operates on scales and in ways that dwarf human experience, where the most ordinary chemical processes can create something extraordinary when taken to cosmic extremes. The next time you see a small diamond glittering in jewelry store light, remember that somewhere in the atmospheres of distant worlds, diamonds might be falling like rain through alien skies, each one formed not in the slow geological processes of Earth, but in the violent, high-pressure cauldrons of ice giant atmospheres, where even the weather is made of treasure. Fact 38. Jupiter acts as a cosmic shield. There's a guardian in our solar system that most people never think about, a massive protector that has been quietly keeping Earth safe for billions of years. Jupiter, that giant striped ball of gas that hangs in our night sky like a bright star, isn't just the largest planet in our solar system, it's also our cosmic bodyguard, standing between us and a universe full of potentially dangerous visitors. To understand Jupiter's protective role, imagine our solar system as a busy cosmic highway, with comets and asteroids traveling along various orbital paths, like cars and trucks moving at different speeds. Some of these objects follow predictable, stable orbits, but others are more like reckless drivers, careening through space on chaotic trajectories that could intersect with Earth's path around the Sun. This is where Jupiter comes in. With a mass more than twice that of all the other planets combined, Jupiter creates an enormous gravitational influence that extends far out into space. It's like having a massive traffic cop stationed at a critical intersection, directing the flow of cosmic debris and keeping the dangerous stuff away from the inner solar system where Earth lives. Jupiter's gravitational field acts in several ways to protect us. Sometimes it captures incoming comets, and entirely, pulling them into orbit around itself or even causing them to crash into its atmosphere. You might remember the spectacular Shoemaker-Lovell 9 comet impact in 1994, when fragments of a comet that had been broken apart by Jupiter's gravity slammed into the giant planet, creating fireballs larger than Earth. That comet could theoretically have been heading toward the inner solar system, but Jupiter intercepted it first. Other times, Jupiter acts more like a cosmic billiard ball, using its gravity to deflect potentially dangerous objects, sending them on new trajectories that carry them away from Earth's neighborhood. It's estimated that Jupiter reduces the number of long-period comets that enter the inner solar system by a factor of about 1,000. But Jupiter's protection isn't perfect, and that's actually important too. If Jupiter were much larger or positioned differently, it might gravitationally dominate the inner solar system so completely that Earth's orbit would be disrupted. If it were much smaller or absent entirely, we'd be bombarded by far more comets, and asteroids than we currently are. The current arrangement seems to be just right. Jupiter is large enough and positioned well enough to deflect most of the really dangerous stuff, but not so dominant that it disrupts the stable orbits of the inner planets. It's what scientists sometimes call the Goldilocks zone of planetary protection. Not too much, not too little, but just right. This protective effect has been crucial for the development of life on Earth. The period from about 4 billion to 3.5 billion years ago is called the Late Heavy Bombardment, when the inner solar system was pummeled by comets and asteroids. Even with Jupiter's protection, Earth was hit frequently during this period, with impacts large enough to vaporize entire oceans and sterilize the surface. But as the solar system settled down and Jupiter's gravitational influence helped clear out much of the remaining debris, the bombardment rate decreased dramatically. This allowed life to get a foothold on Earth and evolve into the complex forms we see today. Without Jupiter's protective influence, Earth might have continued to experience frequent, life-sterilizing impacts that would have prevented complex life from ever developing. There's also evidence that Jupiter's gravitational influence helped deliver some of the water and organic compounds that made life on Earth possible in the first place. While Jupiter protects us from most comets, it occasionally redirects some of them toward the inner solar system in a controlled way. These well-behaved comets, arriving at a manageable rate rather than in a devastating bombardment, might have helped supply Earth with water and the chemical building blocks of life. Recent computer simulations suggest that solar systems with Jupiter-like planets in Jupiter-like orbits are more likely to have habitable rocky planets in their inner regions. This has implications for our search for life elsewhere in the galaxy. When astronomers look for potentially habitable exoplanets, they're also looking for signs of giant planets in the outer regions of those systems, planets that might be serving as cosmic shields for smaller, Earth-like worlds. Jupiter's moons also benefit from this protection. Europa, Ganymede, and Callisto, three of Jupiter's largest moons that may harbor subsurface oceans, exist in a region of space that would be much more dangerous without Jupiter's gravitational influence, cleaning up the neighborhood. But Jupiter's role as a cosmic shield isn't static. As the giant planet slowly migrates in its orbit over millions of years, its protective influence changes too. Computer models suggest that Jupiter's orbit has wandered inward and outward over the history of the solar system, and these changes have affected the impact rate on Earth and the other inner planets. Looking up at Jupiter in the night sky, that steady, bright point of light that's been guiding travelers and inspiring wonder for thousands of years, it's humbling to realize that this distant world has been quietly protecting us all along. Every clear night when Jupiter is visible, you're looking at our solar system's bouncer, the massive guardian that stands between Earth and the cosmic chaos beyond. The next time you spot Jupiter among the stars, take a moment to appreciate not just its beauty, but its role as humanity's protector, the cosmic shield that has helped make our existence possible by keeping the most dangerous visitors from reaching our small blue world. Fact 39. Our solar system moves through space. Right now, as you sit reading this, you're traveling through space at an incredible speed. Not just because Earth is spinning on its axis, or because we're orbiting the Sun, but because our entire solar system, the Sun, all the planets, asteroids, comets, and everything else gravitationally bound to our star, is racing through the galaxy at over 800,000 kilometers per hour. That's about 220 kilometers per second, fast enough to travel from New York to Los Angeles in about 12 seconds. We're all cosmic passengers on a journey, so vast and so fast that it makes every other form of transportation seem like standing still. To understand this motion, picture our galaxy, the Milky Way, as an enormous spiral of stars, gas and dust, slowly rotating like a cosmic pinwheel. Our solar system sits about 26,000 light-years from the galaxy's center, roughly halfway between the center and the outer edge, in what astronomers call the Orion Arm, or local spur, a minor spiral arm that branches off from one of the galaxy's major spiral arms. Just as Earth orbits the Sun, our entire solar system orbits the center of the Milky Way, but this isn't a quick trip around the block. One complete orbit, what astronomers call a galactic year or cosmic year, takes about 225 to 250 million Earth years. Think about that timeline for a moment. The last time our solar system was in its current position relative to the galactic center, dinosaurs didn't exist yet. The most complex life on Earth consisted of simple marine organisms. Pangaea, the supercontinent, was just beginning to break apart. Our solar system has completed only about 20 orbits since it formed 4.5 billion years ago. But our solar system's motion through space isn't just a simple circular orbit. We're also bobbing up and down relative to the galaxy's disk as we travel, like a horse on a cosmic carousel. This vertical motion takes us above and below the galactic plane, in a cycle that lasts about 64 million years. Some scientists have speculated that this bobbing motion might affect Earth's climate, and even mass extinction events. As we pass through regions of the galaxy with different densities of cosmic rays and interstellar material, the motion gets even more complex when you consider that the entire Milky Way galaxy is also moving through space. Our galaxy is part of a local group of galaxies that includes the Andromeda Galaxy, and this whole group is moving toward a gravitational anomaly called the Great Attractor. Meanwhile, the universe itself is expanding, carrying all galaxies away from each other on the largest scales. So right now, you're simultaneously spinning with Earth's rotation at about 1700 kilometers per hour at the equator, orbiting the Sun at about 107,000 kilometers per hour, moving with the solar system around the galaxy at over 800,000 kilometers per hour, moving with the galaxy toward the Great Attractor at about 2 million kilometers per hour, being carried along by the expansion of the universe itself. It's motion within motion like an incredibly complex cosmic dance, where every step is choreographed by gravity and momentum. This grand journey through space has profound implications for Earth and life on our planet. As we travel around the galaxy, we pass through different regions with varying densities of cosmic rays, interstellar dust, and stellar radiation. Some scientists believe these changes might influence Earth's climate over very long timescales, possibly even affecting the evolution of life. We also encounter different neighborhoods of stars during our galactic orbit. Sometimes we're in regions where massive stars explode as supernovae more frequently, bathing our solar system in high-energy radiation. Other times we travel through quieter regions where such events are rare. These varying cosmic environments might have subtle but important effects on Earth's atmosphere and the development of life. The speed of our solar system's motion also means that the night sky is constantly changing, but so slowly that these changes are imperceptible over human lifetimes. The star patterns that guided ancient navigators are essentially the same ones we see today, but over hundreds of thousands of years, our motion through the galaxy will gradually alter the apparent positions of stars. Perhaps most remarkably, this motion means that Earth never travels the same path through space twice. Our planet traces out a complex helical path through the galaxy as it orbits a sun that's simultaneously orbiting the galactic center. We're explorers of cosmic space, constantly moving into regions that Earth has never visited before and will never visit again. There's something both humbling and exhilarating about this perspective. We tend to think of our solar system as a stable, unchanging neighborhood, but we're actually residents of a cosmic nomadic tribe, journeying through the galaxy at tremendous speed, experiencing a universe that's constantly changing around us. The next time you look up at the stars on a clear night, remember that you're not just looking up from a stationary platform, you're looking out from a world that's racing through space at incredible speed, part of a solar system that's on an epic journey through the Milky Way, a journey that began billions of years ago and will continue for billions of years into the future, carrying us to places in the galaxy that no Earth creature has ever seen before. Fact 40. We've only scratched the surface. Here's a humbling thought. Despite all our satellites, space telescopes, and interplanetary missions, despite decades of exploration and discovery, we've barely begun to explore our own solar system. We've sent spacecraft to every planet, landed on several moons, and collected samples from asteroids and comets, yet most of our cosmic neighborhood remains as mysterious today as it was to ancient astronomers who could only dream of visiting other worlds. Consider this. We've had close-up looks at less than 1% of the objects in our solar system. There are likely millions of asteroids, hundreds of thousands of comets, dozens of moons we've never seen clearly, and entire regions of space we've never visited at all. It's like claiming to know a vast city after walking down a few blocks of one neighborhood. Take the Kuiper Belt, that icy realm beyond Neptune, where Pluto lives. This region contains what might be hundreds of thousands of objects larger than 100 kilometers across, and millions of smaller ones, yet we've only gotten close-up images of a handful of them. The New Horizons spacecraft gave us our first detailed look at Pluto in 2015, and then flew by another Kuiper Belt object, Arrokoth, in 2019. That's 2 objects out of potentially hundreds of thousands. Or consider Jupiter's moon. Jupiter has 79 known moons, but we've only studied a few of them in detail: Europa, Io, Ganymede, and Callisto. The four largest have been visited by spacecraft and photographed extensively. But what about the other 75? Most of them are just points of light in our telescopes, barely more than discoveries waiting to be made. Even the planets we think we know well continue to surprise us. Mars, our most studied neighboring planet, still holds countless mysteries. We've been sending missions there for decades, yet we're still discovering new features, still debating whether life ever existed there, still finding geological processes we didn't expect. Saturn's moon Titan, larger than Mercury, has lakes and rivers of liquid methane, weather patterns and possibly even life, but we've barely explored its surface. The Cassini mission gave us tantalizing glimpses, but vast regions of this fascinating world remain unmapped and unknown. And then there are the objects we haven't even discovered yet. Every year astronomers find new asteroids, new comets, new moons around the outer planets. In 2019, they discovered 20 new moons around Saturn. In 2018, they found the most distant object ever observed in our solar system, temporarily nicknamed Far Out. There are likely thousands of objects out there, still waiting to be found. Perhaps most remarkably, every mission we send into space discovers things we didn't expect. The Voyager spacecraft, launched in the 1970s to study the outer planets, kept making surprising discoveries right up until they left the solar system entirely. Volcanic activity on Io, complex ring systems around Jupiter, geysers on Enceladus, bizarre magnetic fields around Uranus. None of these were predicted before we arrived. This pattern of unexpected discovery continues today. The IRIS-REx mission to asteroid Bennu found that the asteroid was ejecting particles into space, something no one anticipated. The Parker Solar Probe, studying the Sun's corona, has already made discoveries about solar wind that are rewriting textbooks. Even our understanding of the solar system's basic structure continues to evolve. The discovery of the Kuiper Belt happened only in the 1990s. The scattered disk, another region of icy objects beyond the Kuiper Belt, was recognized even more recently. There might be entire populations of objects out there that we haven't identified yet. Some scientists believe there might be a ninth planet, not Pluto, but a much larger world orbiting far beyond Neptune. They've inferred its existence from the gravitational effects it seems to have on other distant objects, but they haven't found it yet. Imagine that. There might be a planet larger than Earth, in our own solar system that we've never seen. The deeper we look, the more complex everything becomes. What seemed like simple, dead worlds turn out to have active geology, complex chemistry and possibly even conditions suitable for life. What looked like empty space turns out to be filled with dust, particles and magnetic fields we're only beginning to understand. This ongoing mystery is part of what makes space exploration so exciting. Unlike exploring Earth, where we at least know roughly what we'll find, more land, more ocean, more of the familiar. Exploring space means venturing into truly unknown territory where every new observation might overturn our assumptions. Future missions will undoubtedly reveal even more surprises. Planned missions to Europa will search for life in its subsurface ocean. The James Webb Space Telescope will study the atmospheres of planets around other stars. New missions to Venus will investigate why our twin planet became such a hellish world. But even these ambitious projects will only scratch the surface. There will always be more to discover, more questions to answer, more mysteries to solve. In a sense, we're still in the earliest stages of solar system exploration, like ocean explorers who have just learned to build boats and are taking their first tentative voyages away from the coast. The vastness of what we don't know is both humbling and inspiring. It means that there are discoveries waiting out there that will amaze and surprise us. Phenomena we can't even imagine yet. Worlds that will expand our understanding of what's possible in the universe. So when you look up at the night sky, remember that you're looking at a frontier that's barely been explored, a vast wilderness of worlds waiting to tell us their stories. We've only just begun to scratch the surface of our own cosmic neighborhood, and the adventure of discovery has only just begun.